Hello, everybody. This is Professor Navarro again with Organic Chemistry 1, CHE230, Chapter 8. Now we are going to be working with alkenes. So the time has arrived in which we are going to be finally using all the alkenes we prepared in the previous chapter, Chapter 7b. Right? So in Chapter 7b, what we learned is, well, how to prepare an alkene. So that's going to be our target. We will now do reactions with those alkenes that we made either by E1 or E2 reactions. Everything is really a sequence. So right now, so far, what we have been learning is substitution reaction. After that, we went over the elimination reaction, and now we will learn the addition reactions. Okay? So it's a sequence of events. So right now it's addition to alkenes. Chapter 9 will be addition to alkynes, which are the triple bonds. And then we will finish this course with chapter 10 about radical reactions. Radical reaction is totally different from these particular compounds. That's why we do it towards the end of this semester. Okay, so this one is an overview. Do not get really be afraid or scared by looking at all those reactions. We're going to study all these 10 reactions for this particular chapter. As we see, there is a list here, hydrohalogenation. There is 2 hydrohalogenation reactions. The difference is that one is Markovnikov, the other one is anti-Markovnikov. Markovnikov, anti-Markovnikov is a rule that we will be learning in this chapter. Then we'll have the acid catalyzed hydration, hydroboration, hydrogenation, bromination. More or less by the name, you guys can tell what is happening to the alkene, right? For example, bromination, that means that you're going to have bromines added to the alkenes. Halohydrin, maybe that one you're not that familiar, but halo is a halogen, and hydrin is a hydrate, meaning that you guys will have a halogen and an OH. Dihydroxylation, and dihydroxylation says an anti. That one, we have seen it already in the lab, right? How to get two alcohols, right, adjacent or vicinal OHs. And now we will finally learn how to do the reaction. And we will end with ozonolysis. Okay, so now what do we need to know of all these reactions? Well, first we have to know what they do, the rules behind them, and also the mechanism. Do I need to know all 10 mechanisms? No, I'll tell you right now which ones you have to know the mechanism. You guys have to know the mechanism of the hydrohalogenation, Markovnikov. Okay, you guys need to know the acid catalyzed hydration, only this one. Because in this reaction number 3, there's really 2 reactions. One, the acid catalyzed hydration, and then the second one is the oxymercuration, demercuration. So it's really 11 reactions. But here they're putting together the acid catalyzed hydration and the oxymercuration. These are 2 separate reactions, but out of the 2, the only one that we need to know the mechanism is the acid catalyzed hydration. Next, you guys need to know the bromination. Okay, so here we have 136. Halohydrin formation is very similar to the bromination. There's really no difference between the 2. And that's basically it. I mean, I will then do the halohydrin formation. So 4 mechanisms that we need to know for this particular chapter. Okay, so now, is there any general rule for all these reactions? They all follow the same rule as we will see here on this second slide. It's an addition reaction. What we'll have is an alkene, which is our substrate in this particular case. That's going to be the starting material. And then you're going to be adding the X and Y. They always come in a single molecule. For example, if you're talking about hydration, that would be water. H, that would be the H would be the X, and the Y will be the OH. They're both added to each of the carbons of the alkene, right? Remember, an alkene is composed of 2 carbons. That's where you form the pi bond. So the molecule that's going to be added to the alkene will break up into 2. One will go to one carbon, the other one will go to the other carbon. There are different rules, right? Because at least in this case, and you see it right now in front of you, we have a symmetrical alkene. Symmetrical alkenes, that means that all the branches are the same, right? Or at least there's a plane of symmetry in the alkene, right? I can trace a plane of symmetry right here, and then I can get the same, right? Is symmetrical, right? Based on the alkene. But is that always going to be the case? No. So that's not always not going to be the case. And that's really the challenge, right? I mean, that's how we will come up with the Markovnikov rule. That's coming in a minute. Okay, so here are the general reactions of what we are doing. Hydrohalogenation, remember in the previous slide, hydrohalogenation, you will have HCl or HX, and HX will break up into two. H will go to one carbon and Cl will go to another carbon. In the case of hydration, you have water, H and OH, and they will each go to one of the carbons of the alkene. If you're doing hydrogenation, as the name says, hydrogenation, meaning that you are adding H2. So one hydrogen goes to one, the other hydrogen goes to the other carbon. Okay, so it looks simple because of the reagent, right? That you break it up into two, and then each goes to each carbon. But there are different rules inside. Okay, so some of them, for example, they do carbocations. For example, this one will go under carbocations. So carbocation is an intermediate for this particular step, and we know that carbocations, they will definitely give you CCR. Same thing here. This reaction also it goes through carbocations. Therefore, you will also have CCR in this particular reaction. Halogenation, right? Or what we call bromination, bromination or chlorination. So you guys have Cl2, Cl. It breaks into two. One chlorine goes to one, and the other chlorine goes to the other carbon of the alkene. Halohydrin formation. You guys have an OH and an X, right? So it's a combination of the two species. And finally, the dihydroxylation, you have two OHs, and then they are added to each of the carbons of the alkene. Okay, so once again, it seems simple of what we are doing in this particular chapter. But once again, I mean, is the number, is 11 reactions that we are going to be learning today. And each they have their right? The specifics, right? Special details that we will be covering one by one. But remember that only you guys need to know these four mechanisms, only the ones I circled right here. The acid catalyzed hydration, bromination, which applies also for chlorination, same thing. Halohydrin formation and the hydrohalogenation Markovnikov. Okay? So normally we call this hydrohalogenation with peroxides as well. Instead of calling it anti-Markovnikov, we call it peroxides. Markovnikov is a rule that we will learn in a minute. Okay, so what happens in a addition reaction, right? In addition reaction, we have that the alkene, the double bond, will act as electron-rich species, right? So we know that all these reactions that we're learning are polar reactions, meaning that you will have a nucleophilic center and an electrophilic center. That's always the case. In a polar reaction, that's what will happen. If you look at the alkene is rich in electrons. And also that pi bond is actually kind of unstable, because you can more or less guess that there will be electron-electron repulsion between the sigma and the pi bond, right? Even though that bond exists and makes the bond stronger, but there is also some electron-electron repulsion between those two bonds, right? So that means that the pi bond wants to get more independent. So that means that the alkene will make the pi bond available for an attack. So the alkene can be used as two ways: as a base when it attacks a hydrogen, or as a nucleophile when it attacks an electrophile, right? And those two cases we will see in this particular chapter, that the alkene will act as both. Normally we call it, I mean, it's an electron source. Okay? So the pi bond is an electron pair donor, and it will add as a base or as a nucleophile. So for example, if you look at here, if it attacks the hydrogen, it's a base. But here, if it attacks the X, it would act as a nucleophile. If it attacks here, it would also be a nucleophile, right? So depending on the situation, we always use the pi bond as an electron donor, electron pair donor. Here, why are we using alkenes, right? So maybe this slide would be more useful on chapter 7b to see the application of the alkene. So alkenes that we'll learn how to synthesize on chapter 7b is really opens up all the chemistry, all the industry. That's why oil, the gas prices are going really high, and every single industry is being affected. Transportation, textiles, food industries, agriculture, pesticides, fertilizers, vitamins, all the pharmaceutical companies. Why are they, why is the gas price or the gas industry, so the crude oil industry, so important in the world? Why are there so many conflicts? There are so many wars, like people, like countries like invading other countries because they want to possess particular sources of deposit of crude oil. Is because everything comes from the oil. Petroleum is the one that contains all these particular compounds, and the industry will definitely use them. For example, alkenes alone, you can produce aldehyde. Acetaldehyde is used in the industry. Formaldehyde, all those essences like smells, colors, all those colors are coming. The textile industry, dye industry, the hair coloring industry, they need these aldehydes. It's coming from who? It's coming from alkenes. Where is alkenes coming from? From crude oil. Same thing with ethylene chloride. Most of the pesticides are chlorinated. So where are these chlorinated compounds coming from? Alkenes. And alkenes come from crude oil. Epoxides, yeah, those are the resins. All those adhesives that you use, glues, all those resins are coming from epoxides. This epoxide resin that is coming from the alkene. Same thing, alcohols. All this is isopropanol, rubbing alcohol. So all those alcohols that we've been using as a solvent or as a fuel, right? All those are also coming from from an alkene. Ketones are good solvents, so they're excellent solvents. They don't really oxidize or anything. They're really semi-polar, right? So not so polar, not so non-polar. So they're also made from alkenes. So you see the richness of the alkenes is really diverse. You can synthesize basically any single organic functional group in organic chemistry that you desire. Okay, so that's the importance of the alkenes, and we will use them to synthesize many compounds. So 7b is a key chapter because it opens the door for chapter 8. And chapter 8 will also open the door for chapter 9, which is alkynes, right? Very similar reactions. And also don't panic really with the reaction. You will say, oh, professor, that means that on chapter 9, I have to learn another 11 reactions. No, most of the reactions from chapter 8 are being repeated on chapter 9. So you don't really have to learn a new stuff, a new reaction. Normally, for example, if I'm talking about hydrohalogenation of alkenes, you will also have a hydrohalogenation of alkynes. It's the same reaction, only applied to alkynes. Hydrogenation of alkenes. Yes, you also have a hydrogenation of alkynes. Exactly the same reaction. Are they having the same mechanism? Yes, 90% in common. The mechanism is identical. Same thing with HBr, right? So halogenation, hydration reactions, they're all the same. So don't think that now chapter 8 and 9 are going to be really heavy. 8 would be heavy because this one is the first chapter you're going to be encountering, and you guys have to learn 11 reactions in one shot. It's 11 reactions on this chapter. Next chapter, it will be about the same number. Chapter 9, you will have about 9 or 8 reactions. But out of those 9 or 8 reactions, 7 of them, or almost 8 of them, are the same that you learn on chapter 8. Okay, so this slide really introduces you to the world of the alkene chemistry. Alkenes, they can be converted into many functional groups. And then how are we going to make that conversion? By using this reaction that we were learning today. Definitely there are many more, but here are the most important. Okay, so why alkenes? Alkenes are very important, right? So it's also very important to learn how to name them. So naming of alkenes is really similar to what we learned on chapter 3. Chapter 3, chapter 3, not chapter 4, right? You will recall about naming. Remember the naming, the longest continuous chain, number the chain from the closest end, right, to that is closer to one substituent. Then you guys have to name substituents. In some cases, you might have substituents, right? And then you have to go by alphabet, right, doing the naming. The same rules that we have for back then on chapter 3 and 4, those rules will also be used for alkene nomenclature. Okay, so now, but the difference is that now you will change the ending. For example, if something used to be called pentane, now it's going to be called pentene. If something you call it cyclohexane, now it will be called cyclohexene. Okay, and the same thing will apply for alkynes. So cyclohexene, cyclohexine, right? Butene, butine, right? So is the ending the only thing that changes, but the rules are exactly the same. So here are the rules, basically just brushing up of the rules, but let's just go directly to the slide, right, or to the basically to the meat, right, of this particular task or this particular section. Pentane, pentene. Do I have to use any numbering? No, in this case, I don't need to number it. Why? Because the alkene of some carbon number 1. So if you don't see any number here, you can assume that here is supposed to be 1 pentene. Now, another thing that for alkenes, you might think like, oh, the alkene is between carbon number 1 and 2. Do I have to say 1, 2? No, you don't need to say 1, 2. You only need to number the alkene based on the first carbon. You don't have to say 1, 2 pentene. You only have to use 1. So because the alkene starts on carbon number 1. So technically this molecule should be called 1 pentene. But if you don't see a number, then you have to assume that it is on carbon number 1. Okay, so that's why in this case, they only just use plain flat pentene. Why? Because by telling you that it is going to be, what is going to be on the first carbon. It could be another case. This one would be, what would be the name for this? For this compound would be 1, 2, 3, 4, 5. So in this case, I will have to call it 2-pentene. Do I have to use here the 2? Yes, in this case, you have to say the 2. Because if you omit the number 2, then you will be assuming that it's on carbon number 1. So you have to be really specific by saying 2-pentene. So here is the parent chain, right? So what happens if I have branches? Well, if you have branches, then you have to choose the longest continuous chain that includes the double bond. You have to make sure that your double bond is in the longest continuous chain. Oh, what about if my longest chain is not doesn't have a double bond? No, you have to choose the longest continuous chain that includes the double bonds. For example, here is 1, 2, 3, 4, 5, 6, 7, 8, right? 8 carbons here. That's my longest continuous chain. But is this longest continuous chain containing the alkene? No. So 1, 2, 3, 4, 5, 6, 7, 8. But my longest continuous chain with the alkene will be 1, 2, 3, 4, 5, 6, 7. 7 wins over 8. Why? Because it contains the double bond. You always have to choose the longest continuous chain that has the double bond. What if I have 2 double bonds? Is it a compound that can have 2 double bonds? Yes. So make sure that also your longest continuous chain contains both double bonds. Okay. So there will be very few exceptions that we have 2 double bonds, but it is doable. Also, don't forget that alkenes, they can also have the cis and trans configuration. So if you have cis and trans, in this case, cis and trans doesn't apply. But let's say if I have that compound that I was using as an example, right? I will have to call it trans 2-pentene. This compound that we used before, it would be trans 2-pentene. Why? What would be, how would it look like the cis 1-pentene? If you have the cis 1-pentene, 1, 2, 3, 4, yeah, that would be the cis. That would be the cis 2-pentene. So you guys have to be specific with the cis and trans. In some cases it applies, in some cases it doesn't apply. Do I have to use cis and trans? No, you can also use the E and the C configuration, right? Remember from the previous chapter 6, I believe. So, or 5, chapter 5 or 6, we use the E and the C. So those items should also be included. So for example, here, I will use trans. Trans should be included in the name, or I could use the E, right? So in that name, let me see that name for this compound. It would be 5,5,6 trimethyl 2-pentene. Heptene, right? Because my longest continuous chain is 7, heptene. But I have to put on the beginning the word E, 5,5,6 trimethyl 2-heptene. Okay? So that is what they have, right? So there are 2 ways how to name it, trimethyl 2-heptene, or you can put the 2 in the middle. So instead of calling it 2-heptene, you can break the heptene into 2 parts and call it hept2-ene. So meaning that the 2 applies to the ene. Remember, the ene is the ending for alkenes. Okay, so here's exactly what I was mentioning, that they have to, they're showing the configuration, right? The stereochemistry is also included on the name. Yep. So, okay, so let's see if we can do a few examples here for naming. Okay, so let's say that I have. Okay, so this particular compound, they give me this compound and they tell me, okay, so name it, right? I want to name it. Okay, so you want to name it, then you have to look find the longest continuous chain that includes the double bond. 1, 2, 3, 4, 5, 6, 7. Yes. Okay, so 1, 2, 3, 4, 5, 6, 7. So one. Oh, and then I have to number it. 1, 2, 3, 4, 5, double bond. 1, 2, double bond. Okay, now who gets priority? Double bond or substituent? Double bond, of course. Double bond has more priority. What if I have a tie, right? So for example, here I have a double bond and here I have a Cl. 1, 2, double bond. 1, 2, substituent. Which one wins? Of course, double bond wins. What about if you don't have, right? I mean, if the double bond is, let's say, carbon number 3, and the substituent is on carbon number 2, you still use the double bond. Double bond has more priority than the substituent. Okay, so that's a rule that double bond is the one that gets the priority over the substituent. It's a functional group. Functional group will always get priority over double bonds. Sorry, over substituents. Okay, so my numbering would be here. Let's do 1, 2, 3, 4, 5, 6, 7. I don't have substituent or substituents. Okay, that's good. Okay, most likely I won't give you a hard time substituting or substituent when you guys do alkenes. We passed that already. Okay, substituents, chloro. And what do I have here? I have here a methyl. Okay, so I have the 2. Sorry, my ink is about to go. I want to, because it's a BMCC pen. Okay. So substituents, chloro by alphabet, chloro goes before methyl, 4 chloro, 2 methyl. Then what comes? The alkene. Then comes the name of the alkene. The alkene is a carbon number 2. So 2, it has 7 carbons, heptene. Okay, the name 4 chloro, 2 methyl, 2 heptene. Can I put the heptene, the hep2 in? Right, yeah, it's up to you. Normally, personally, I prefer like that, 2 heptene. The 2 applies to the in, right? Because that every number always refers to something, right? 4 chloro, it's telling me that the chloro is on carbon number 4. 2 methyl, the methyl is on carbon number 2. 2 heptene, that means that the in is on carbon number 2. Of course, I'm not gonna read it as hept is on carbon number 2. No, because that one is a numerical prefix, right? This one is a functional group ending. And now I have to add the stereochemistry. Okay, so here I have a methyl, 2 methyls. I cannot distinguish between E and Z, and I cannot distinguish between cis and trans. I'll just leave it like that. I don't need to add anything. Because there's 2 methyls. This methyl, right? If I want to assign priorities, both methyls, I cannot do priorities because they're identical. Between here, yes, because here is a hydrogen that I don't see. Here will be a priority, but here I cannot distinguish priority, so I cannot apply EZ. EZ is done. I can. What about the cis and trans? No, because I don't have twins. I need twins, right, to determine what type of if you have cis and trans. But here I don't have. Okay, so no cis trans, no EZ. So I'll just leave it like this. What about with rings? Okay, my longest continuous chain is the ring, the cyclopentane, right? Cyclopentane, the five-member rings. I should start numbering with the double bond. The double bond is the one that gets priority, but always remember that I have to go, whenever you guys number double bonds in a ring, you have to go by the double bond. You cannot do like 1, 2. No, you have to do 1, 2. Your 1, 2 should go by the double bond. So in this case, I have to decide if I do 1, 2, 3, or I do 1, 2, 3, 4, 5. Of course, it's more convenient for me to go this way. Why? Because if I go this way, I'm closer to the substituents. I'm still passing by the double bond. The double bond is really not an issue. It's the substituent. So I will say 1, 2, 3, 4, 5. So my substituents are methyls, right? 3, 3, 3,3 dimethyl. That's it, right? So those are my substituents. Then I have the It's on carbon number 1. I mean, doesn't hurt. 1 cyclopentene. Right? Because you might say, like, oh, professor, in the previous slide, you say that if you don't mention the number, right? So you can assume that it's located on carbon number 1. Yes, it is. It is. I mean, you can omit it, but I don't know. Maybe it's just by default that I adding one, like 3,3-dimethyl 1-cyclopentene. Is it correct if you write 3,3-dimethyl cyclopentene? Yes, because if you omit it, you are assuming that it's located in carbon number 1. Now, do I need to specify the cis and trans? In this case, my hydrogens are cis, right? Or I could call it a C alkene. But whenever you guys have rings, right? If it's rings of 4, I think 3 to 7, there is no need to specify. Always the double bonds are going to be cis. There is no way you can have a trans double bond in a ring that is 3, 4, 5, 6, or 7 member rings. Okay, so in this case, even though it's a cis, but you don't need to say it. Why? Because cyclopentenes, right? Cyclopentene by default, they are cis. Same as cyclopropane, cyclobutene, cyclopentene, cyclohexene, and cycloheptene. Those 5 are cis by default. You don't need to specify. What about for cyclooctene? Yeah, in cyclooctene, you have to mention that there are cis or trans. Cyclononene, yeah, you have to mention if there are cis and trans. Okay, so 3 member rings to 7 member rings, you don't need to indicate cis and trans. Cis and trans by default, they're always cis. Okay, all right. So more examples. I mean, we will have it in the solve problem videos, but now let's go back to the slides. Okay, so these are the rules for the E and C. I didn't do it. Well, yeah. Let's do one for E and C. Yeah, maybe we should do that. One example that you guys apply E and C configuration. Let's do one last example. Let's say that I have. Okay, I have this compound, and they tell me, let's put here. Okay, good. All right. Okay, so let's see here. Longest continuous chain. Okay, so remember the longest continuous chain that goes through the double bonds. In this case, I have 2 double bonds. So I will do my best to fit or to adjust or to include those 2 double bonds in my chain, right? So 1, 2, 3, 4, 5, 6, 7. Good. 1, 2, 3, 4, 5, 6, 7, 8. Okay, so here I have 8, but it doesn't include the 2 double bonds. It only includes 1. If I go this way, it's 7, but it includes both of them. If I do 1, 2, 3, 4, 5, 6, 7, 7, but also 1 double bond. So which one should I decide? So I will always decide the longest continuous chain that includes the maximum number of double bonds. In this case, I can include 2 double bonds. So I will choose that as my longest continuous chain. My longest continuous chain is right here. Just graying it out. Okay, so that's my longest continuous chain. It's not the longest, absolute longest, but it's the longest continuous chain that contains the maximum number of alkenes. Okay? So that's, I just want to be very specific with that. Now the numbering, should I start numbering from this end? 1, 2, 3, double bond. 1, here my double bond is already on carbon number 1. Some students might get confused. You will say like, oh, fluorine should get number 1. No, it has to be you. Number 1 has to be a carbon. And here there is no carbon. This one is a fluorine. So my first carbon will be right here. This will be numbering 1, 2, 3, 4, 5, 6, and 7. Okay? So that's are the numbers for my double bonds. Sorry, for my longest continuous chain. Now I have to name the substituents. Here I have a fluoro. Here I have an ethyl. Here I have another ethyl. Here I have a bromine. That's it. Right. So let's say that the name for this compound, if I go by alphabet, bromo wins. 5-bromo. Right? Next in alphabet, E, right? 2,3-diethyl. What else? Fluoro in carbon number 1, 1-fluoro. Okay. And then the main chain. The main chain is called heptene, right? But in this case, I have two double bonds. So what should I do when I have two double bonds? Where are the locants, the locations? 1 and 4, right? That's the location for the double bond, 1 and 4. No 5, it's 4, right? It's the first carbon of the double bond. 1, 4, 1, comma 4. I don't know why I keep doing dashes. 1, 4, heptadiene. Why is it diene? Because it's two of them. If it would be one, it will only be heptene. But since it is two double bonds, it's heptadiene. Why hepta? Why not hepdyne? It is just phonetics. I mean, I've been used to that. I mean, it is always put a vowel in between, heptadiene. Or what about if it's hexa? Yeah, hexadiene, pentadiene, octadiene, butadiene, right? So it's always the A. The A is added. It's just something with phonetics, really. That A doesn't mean anything. It's just to space the, I guess, is the sound, something like that, to be honest. Okay. What if I have three double bonds? It will be heptatrine, right? 3 trine, heptatrine, heptatetrine. Tetra is for 4. Tetrine, right? If you have more double bonds. Okay? So 1, 4 heptadiene in this particular case. All right, so I'm done with the name, but now I have to deal with the stereochemistry. So let's see here. So how is this a cis or a trans? I cannot use cis and trans because all 4 groups are different. I'm looking at this double bond. So here I have a hydrogen. Between this hydrogen and fluorine, fluorine gets priority. And between the ethyl and this group that has more carbons, definitely this group gets priority. So the 2 heaviest or the 2 highest priority, right, of the 2 are trans. Therefore, this compound is going to have 1 E. Why are you putting 1 E, Professor? Because the double bond is located, that E is for the double bond that is located on carbon number 1. 1 E. This one is E. This one is 4. Because that double bond is located on carbon number 4. Don't put 1, 2. You have to put 1 E, 4, whatever it is. Let's see. H, this one is my priority. And here between bromine and carbon, bromine wins. That is a Z. 1 E, 4 Z, 5 bromo, 2, 3 diethyl, 1 fluoro, 1, 4 heptadiene. So that would be the name. So and then next time that you go to Stackroom, please ask for 1 E, 4 Z, 5 bromo, 2, 3 diethyl, 1 fluoro, 1, 4 heptadiene. So, and that's this compound if you want to make it anytime, right? So that's something that we need to include. Okay, I just want to be clear once again what happened with the 1E and the 4C. The 1 is coming because of the double bond. The double bond, that the 1 that doesn't mean the first. That means that the double bond is located on carbon number 1. And then, of course, these numbers should match this, right? 1, 4, 1, and 4, where the double bonds are located. So 1 is E, is an E alkene, and Z is on carbon number 4. Once again, for if you guys want to brush up of EC configuration, please go to chapter 5. We went over about how to do the E and C configuration for an alkene. Right. So that was the example. So now let's continue with the reactions. All right. So now we have the reaction. Now that we know how to do the naming, let's start with the reactions, right? So what is the thermodynamics, right? Of why is it driven, this reaction? Why is this reaction successful? Remember that any reaction really has 2 paths, right? Or 2 things to take into consideration. One is the enthalpy, which is the one that we are seeing right now, right? Enthalpy right here. And the next one is going to be the entropy. Okay, so what is the enthalpy telling me? The enthalpy is telling me that the reaction is favorable. Why? Because you are sacrificing a pi bond, which is high energy, to create 2 single bonds. That's good, because sigma bonds are more stable than pi. So you are sacrificing a pi to create 2 more stable sigma bonds. Okay, so sigma bonds are stronger, more stable than pi bonds. Pi bonds are very reactive. Remember that the pi bond is formed by through distance, right? Overlap. The orbitals are not overlapping. They're not physically touching. They're only close enough so the spins, right, they have some attraction. There is an attraction force between those electrons, but they never see each other. They never touch. It's just an attraction between those electrons that have different spins, right, opposite spins. So those bonds that are pi So they are not as stable. And also they create electron-electron repulsion. So a sigma bond doesn't have electron-electron repulsion when they are alone. So that's why we see here that the sigma bonds are more stable. So from the enthalpy point of view, the reaction is good. Now what happens, don't worry about I'm not gonna ask you how to do the math, right? Or how to determine the delta H of the reaction. We did that already on chapter 6. For these chapters 8 and for any other chapter, we are not going to determine the enthalpy. This is only for you guys to see that the reaction has a spontaneous or a favorable enthalpy. Okay? But I'm not going to ask you about determining the enthalpy of the reaction. Now, what happens in the entropy, right? In the entropy, the reaction is not favorable. It's not good. Why? Because you are combining an alkene and another compound. That compound is going to be added to the alkene. So you have two compounds, two molecules, molecule here, and they're going to be merging, they will merge into one single product. From the entropy point of view, that's not good. Okay, and what is the other thing is that most of these compounds are also gases. So you're converting a gas into a solid or a liquid. That's also bad from the entropy point of view, right? So remember, entropy wants chaos, wants disorder. If you convert a gas into a solid or a liquid, you are decreasing really the entropy. Nature doesn't like that. So, but how do you compensate that loss of entropy? By having a good enthalpy, right? So remember, there is an equation that says that delta G is equal to delta H minus T delta S. So even though you have a unfavorable entropy, but you can have a favorable enthalpy, that's how you compensate that lack of energy, right? The contribution. Okay, so just keep that in mind that entropically wise, right? Entropy wise, the reaction is not favorable, that the enthalpy says yes. Okay, okay, ready for the first reaction? Okay, so let's start with the hydrohalogenation. Is the first reaction we're going to be learning. Here we will learn the Markovnikov addition, Markovnikov rule. But first I would like to start, we have an example. We have this particular alkene. This alkene is a cis. You can see that the molecule is symmetrical. Okay, symmetrical because you have an ethyl on one side, the ethyl on the other side. They're both the same, so you can trace a plane of symmetry. If you do an HBr, of course, the HBr will be broken up into two fragments. One will go to one H and the Br will go to the other H. Okay, I'm not doing the mechanism. I'm just doing a scheme of what happens. The HBr will break into two and each of these fragments will go to the alkene, added to the alkene, and you get a reaction of 76%. Since all these molecules are in the gas phase, HBr is a liquid. I mean, we use that in the lab, but HBr is a liquid, but the alkene, this alkene most likely is a gas. That's why we have to do the reaction at minus 30%, sorry, minus 30 Celsius degrees. You get 76% of yield. Is a high yield reaction, mostly for considering a gas phase reaction. So therefore, I mean, the reaction proceeds. What happens if the alkene is not symmetrical? Then you guys have two potential regioisomers. Okay, why? Because you can have, if you have this position, you can have the H going here and the X going here. But what is the other option? The other option is that the opposite happens. What is the opposite? The opposite is that the H goes here and the X goes here, right? It's not the same thing. You will definitely get different products. So is there any rule that tells me which one is preferred? Is it preferred the blue arrows or is it preferred the red arrows? That one, the only thing how to see it is through the mechanism. Okay, so the mechanism is the one that's going to tell you, and that is going to be called the Markovnikov rule, or what we call the Markovnikov addition. The Markovnikov, what it says is that the nucleophile goes to the most substituted carbon. In this case, they say the halogen, but here we will call it the halogen, the nucleophile. Anytime that you guys are doing an addition, you always have to think that the nucleophile will go to the most substituted carbon of the alkene. In this case, if I have an unsymmetrical alkene, this one is my most substituted. Therefore, if I do HBr, the Br, which is the nucleophile, will be added to this carbon, and the H will be to this carbon, not the other way around. Okay, so they observe that Br is installed here, so it is added there. What is the opposite? The opposite is called the anti-Markovnikov. Not all the reactions follow the anti-Markovnikov. All the reactions will follow the Markovnikov. There are only, out of those 11 reactions that we mentioned, only 2 of them follow the anti-Markovnikov. Anybody else, I mean, any other reaction will always do Markovnikov. Okay, so by default, Markovnikov should be your rule of thumb. Right? So you guys have to follow always the Markovnikov. Only those 2 reactions will be anti-Markovnikov, but anything else is going to be Markovnikov. Okay, so let's see how it works, right? So here now is the mechanism. Oh, there is another one, the hydrohalogenation with peroxide. But first, I want to explain you why follows the Markovnikov rule. Okay? So let's say here hydrohalogenation. I'm gonna fix this one in a minute. Just give me a minute. Focus. Okay. Hydrohalogenation in this reaction allows you to add HCl, HBr, and HI. What about HF? Can I add HF? No, because right, I think from the very beginning, from chapter 7, we were saying that F is really a bad, well, it's a bad word, but also it's a bad element for right, for organic chemistry. Normally there is a special, even I have seen some books called about fluorine chemistry, organic chemistry of fluorine, that they see all the specifics of fluorine. Fluorine is a very complicated atom for organic chemistry because of the electronegativity, also because of the size, because of the, let's say, solubility problems that it has. It's very complicated. So that's why all the reactions that we normally analyze exclude the fluorine as a halogen. Normally we do HCl, HBr, and HI. Okay, so the mechanism for hydrohalogenation. Let's do the mechanism, how it happens. Let's do with a simple alkene, a symmetrical alkene in this case. Let's use HCl. Okay. So we were saying that the alkene is an electron rich. Here in the HCl, as we know, it is divided into delta plus and delta minus. So you can here determine that this H is going to be your electrophilic center and the Cl is the nucleophilic center. Because it's delta plus and delta minus. Okay. So the alkene is electron rich, has to attack the electron poor. In HCl is going to attack the H, has to attack the H, the double bond. Look at how I do the arrow. The arrow has to be from the pi bond. Don't do the arrow from the carbon, from this sigma, no. Has to be from the alkene to the H. What happened with the Cl? The Cl is a leaving group in this particular case, right? I mean, it just dissociates, it just breaks apart. What happens here? Now, since the alkene is symmetrical, it doesn't matter where I put the carbocation. The carbocation can be here or can be here. Why again? Because my molecule is symmetrical. Both of them have the same branching. One branch, same. And then methyl, same particular substituent. So it is exactly the same. So the H will be added to one of them. What happens with the other carbon? The other carbon lost the pi bond. Now it becomes a carbocation. See? The H is taken by the alkene and then sits on this particular carbon. That carbon, I mean, since the alkene is symmetrical, it doesn't matter where you put the hydrogen. I put it here, but I could have done it here as well because the alkene is symmetrical. Okay, carbocation. Anytime that you guys have a carbocation, you guys can have to ask about CCR. Always, carbocation is a synonym of CCR. Secondary carbocation, primary, secondary. So no CCR. So next is the nucleophilic attack. Who is going to attack? The chloride. Chloride is around, so chloride is going to attack the carbocation. Okay. Now, am I going to get one single product or two products? Well, anytime that you guys have carbocation, you always have to think of racemic. Why? Because remember that the carbocations, they have those two. I'm going to do it. I'm going to use it here. You have a carbocation. You guys have the p orbital, and the chlorine can attack this upper lobe or this bottom lobe. Right? So that's what happens with a carbocation. Right? So it has the p orbital, and the p orbital can be attacked in two different phases. Same thing happens here. In this case, my carbocation is prochiral. So why is it prochiral? Because it has a methyl, has an ethyl, and has a hydrogen. So it's 3 different groups on the carbocation. If it has 3 different groups, it is prochiral, meaning that if the chlorine comes in, it will be chiral. So you guys will have this compound. Is this carbon chiral? Yes, this is chiral. So if it's chiral, you guys will produce 2 products, that and this one. Okay? Why? Because it's a carbocation. It has the 2 lobes. You can attack the bottom or you can attack the top. Do I have to show the mechanism for both attacks? No, only one. So and then you're gonna write this plus this. You can write the 2 products, or you can write only this and then write here the word plus stereoisomer. Any of the 2 options that you consider more appropriate. Okay. Don't write enantiomer, because sometimes it's not only enantiomer. It is the enantiomer respect to the carbon. But what if you have a second chiral center here? It's not going to be the enantiomer. It's going to be the diastereomer. So for you guys to save the time to analyze if the molecules are enantiomers or diastereomers, just write it simply as stereoisomer. Or what if it's a diastereomer and I made a mistake, and then it actually is a diastereomer or enantiomer or diastereomer, right? I made a mistake labeling. Am I gonna get points off? Unfortunately, yes. So that's why please just use the word stereoisomer, because that's the one that is more general for these particular cases. All right. So that would be the mechanism for the HCl. So as you can see, it's very simple, very straightforward. Let's do one that has carbocation arrangement. And also let's see what, actually let's do one with the Markovnikov. Okay. So let's do an HBr addition with Markovnikov. That we actually see the Markovnikov rule. Okay? So let's see that I have this. Now I have an unsymmetrical alkene. This alkene will be called, I'll give you 3 seconds. 1, 2, 3. Correct. This alkene is called 1-butene, right? Or you can just simply call it butene. 1, 2, 3, 4, butene. Okay? All right. So this butene is reacting with HBr. As we know, HBr has delta plus, delta minus. Definitely the H is going to be attacked by the alkene. Alkene attacks the H, bromine leaves. Okay, so now you guys have 2 options. The H can go here on carbon number 1, or it could go on carbon number 2. Let's see what happens. Let's put it on carbon number 1. That means if you put the hydrogen on carbon number 1, that means that the carbocation will be on carbon number 2. If you do the other addition, I mean the other way, so that means that the hydrogen goes to the carbon number 2 and the carbocation will be on carbon number 1. Those are the 2 carbocations that you are producing. I will put where the hydrogen is so you guys can see, you don't get lost. Okay, so that's my carbon number 1. I put the labels here, 1 and 2, 1 and 2. Okay? 1 and 2, 1 and 2. It's the same 1 and 2. I'm putting the hydrogen carbon number 1 and the hydrogen here on carbon number 2. The carbocations are also here on number 2 and here on number 1. Now the question is, like, you guys that you know are experts in carbocations, which of these 2 carbocations is more stable? Correct. Yes. Secondary carbocations are more stable than primary carbocations. Okay. So should I do this analysis before or after CCR? I should do this analysis after CCR. In this case, I don't have CCR. Well, here it will be CCR, but if you do CCR, you actually end up being here. But the thing is that primary carbocations, they don't really exist, right? I mean, highly unstable. Between this primary and this secondary carbocation, definitely this one is more stable. So if you ask bromine, which one do you prefer to react with? Of course, the bromine is going to tell you, I prefer to react with the most stable. Because this one is very reactive. I mean, it's not going to exist. This reaction will go back to the starting point. It's not going to exist. So bromide will say like, well, I want to react with the most stable. Definitely. I will do the attack here. And the attack, of course, this one is a most stable carbocation. The reaction will go through that side. So you guys will get the bromine here. Bromine attacks and is added to that carbon. There is no CCR. secondary carbocation, secondary carbon, primary carbon, no CCR, and I get this compound. This compound is chiral. That's why I say like with the wedge plus the stereoisomer. Am I gonna be producing any of this compound? No, this one is not obtained. Okay, what is the name of this rule? As you can see, the nucleophile, which is the bromine is a nucleophile, is added to the most substituted carbon of the alkene, number 2. That is what Markovnikov says. Markovnikov says that in an addition reaction to alkenes, the nucleophile adds to the most substituted carbon of the alkene. Okay. Okay, or you could also say like, oh, in this hydrohalogenation, the H goes to the least, right? The electrophile goes to the least substituted. Or you could say like the nucleophile goes to the most substituted carbon of the alkene, right? Any of the two ways. So that is what we call it the Markovnikov rule. Markovnikov, he was a scientist, an organic chemist. He surveyed a lot of alkenes, and he noticed that always the nucleophile adds to the most substituted carbon of the alkene. He didn't observe much. He didn't observe this product. He only observed this product. He didn't observe that one. Okay? So that is called the Markovnikov rule. Okay, so let's do one mechanism or a reaction with migration. Okay, so let's see that I have this compound alkene here. Okay, and then I'm adding HI. Okay, great. I know the Markovnikov, right? This HI is Markovnikov. This reaction follows Markovnikov. So I know that this one is my Markovnikov carbon because it's the most substituted. That means that the iodine will most likely go here. But let's see, because remember, this reaction goes through carbocations. It could be a CCR involved. Okay, so let's see, alkene attacks H, and then I leaves. H goes to the least, carbocation on the most, substituted. I get this carbocation. What happened with the iodine? The iodine is somewhere, right? Somewhere here in the solution. What happens here whenever you guys produce a carbocation? You have to ask if this carbocation will undergo CCR. And in this case, it does, right? So in this case, you see secondary carbocation, primary carbon, tertiary carbon. Can I do CCR? Yes, I can do CCR. The H migrates. The H migrates, and then I have a new carbocation right there. This carbocation is the one that you have to. Now, did I use Markovnikov before or after? I used the before CCR, right? I think here I said after, right? After CCR. What I really meant is that the nucleophile addition is done after the CCR, not the Markovnikov. The Markovnikov, it is done as soon as you attack the hydrogen or you attack the electrophile. The first attack of the alkene, that's when you guys decide which one is the Markovnikov or no Markovnikov. This is Markovnikov, this is anti-Markovnikov. You decide that on the alkene by looking at the alkene, not after CCR. I made a mistake. Not after CCR. You guys have to decide which one is your Markovnikov or anti-Markovnikov as you see it on the alkene. So in this case, I see the alkene. This one is my Markovnikov carbon. This one is my anti-Markovnikov carbon. So here's where I decide Markovnikov. That's where you put the carbocation. And then you do CCR if it applies. If it applies. Okay, so I have the carbocation after CCR, and then here I do the nucleophilic attack. Iodine, right? Iodine attacks. This, I'm lucky because this particular carbocation is not prochiral. That means that the iodine will attack to only one, producing one single product. Iodine there, that's my product for this reaction. Okay, so I do get CCR because it goes through carbocations. Okay, good. So we checked off the first mechanism, which is hydrohalogenation. Well, let's go back to the slides to see what they have to show us. Okay, so there is radioselectivity. It's not specific, right? So remember from chapter 7b, there is a difference between radioselectivity and radiospecificity. It's selectivity, meaning that the major product is going to be is going to be the Markovnikov, the most, right, the most saturated carbon. You still get the other one, but in very, very minor percentage, okay? So that's the Markovnikov. Let's see, let's continue with the next slide, right? The second reaction, this one, we don't need to do the mechanism. This mechanism, we will learn it on chapter 10. Right now, don't worry about chapter 10. It's too early to be worried about chapter 10. Let's first finish with chapter 8, right? So this hydrohalogenation, as you can see, is the same reaction, HBr, but the difference is that now it's in the presence of peroxides. What is peroxides doing? Why peroxide changes the stereo, right? The stereochemistry of the reaction. Because this reaction, I'll just give you a preview. This reaction goes through radical mechanism. HBr regular, this HBr goes through a polar mechanism. This one is a polar mechanism because you guys are using delta plus, delta minuses, right? Electron rich, electron poor. Here in this reaction, you are using radicals. Radical is a species that has an ampere electron. It's a totally different system for mechanism, right? So HBr in peroxides uses a radical mechanism. That's why it has the opposite regioselectivity. So if you have this alkene, this one is my Markovnikov center, and this one is my anti-Markovnikov center. HBr in peroxide will add the nucleophile to the least substituted. In Markovnikov, is the opposite. The bromine goes to the most substituted. Okay, so bromine goes to the most substituted. In this case, bromine goes to the least substituted. 95%. You can see that it's a very clean reaction. Okay, the reaction mechanism must be different, of course, because when peroxides are present. So whenever you guys see an HX, right, HBr, HCl, normally I have, to be honest, I have only seen it in HCl and HBr. I haven't seen this reaction with HI, like with H iodine. Let's just restrict it to HCl and HBr. Okay? So you have to always watch out for the presence of peroxides. Sometimes they call it H2 hydrogen peroxide, but I have seen it more with organic peroxides. That could be a dimethyl peroxide, right? That's the peroxide functionality, by the way. Oxygen and oxygen. So that peroxide is, I mean, it's an oxidant, so it is really, the mechanism is still, and it's not that clear. I mean, it is clear. We will do that mechanism on chapter 10, but it goes through radicals, definitely. Okay, so do we need to know that mechanism? Not now, but we need to know that it goes through anti-Markovnikov. Okay, so here, just to summarize this hydrohalogenation, we have two types of hydrohalogenation, HBr alone that follows Markovnikov, and we also have the HBr with peroxide that follows the anti-Markovnikov. Two different ways how to do hydrohalogenation. Very specific, with very high yields for Markovnikov, and also very high yield for anti-Markovnikov for this second reaction, okay? So remember that the Markovnikov and anti-Markovnikov only can be applied if you have unsymmetrical alkenes. Now, I want to take advantage of this particular reaction, so I can also tell you something, right? So, or some exceptions. You know, organic chemistry is the kingdom of the exceptions. What to do? Okay, so what to do if I have this alkene? Let's say I have HBr. Okay, you will tell me, okay, professor, well, according to what you told me, HBr follows Markovnikov. Okay, good. Okay, label the Markovnikov carbon here. Which one is more substituted or less substituted? This carbon has one substituent, one branch. This carbon also has one branch. They both have one branch. Which one is Markovnikov? Which one is anti-Markovnikov? None of them. There is no Markovnikov, there is no anti-Markovnikov carbon. So that means that I cannot do the reaction. You can, but you will get a mixture. Because since they are both Markovnikov, they are also both anti-Markovnikov. So you will just do the reaction. You actually will get two products. You will get the product that has the bromine here. And you also get the other one that has the bromine here. Plus the stereoisomer, right? You will get both. Why? Because there is no, HBr follows Markovnikov, but once it meets a molecule that cannot distinguish between Markovnikov and Markovnikov, you will get two products, two sets, addition here and addition here. Nucleophile here, nucleophile here. Obviously, like, oh, but professor, maybe because this is an ethyl, it will be a major product, maybe? No, it doesn't go by that. the bromine doesn't know who is coming next. The bromine just attacks alkene, regardless of who is outside. Maybe here you have 100 carbon chain, and here you have only 2 carbon chain. That doesn't matter for the bromine. The bromine only adds to the carbons. It doesn't add to the tail, doesn't add to the dress of the carbon. No, it only attacks the alkene, regardless of what is around here. So it only counts the number of branches. Okay, so no matter what branches you have, even if it's bulky, tertiary, resonance, right, doesn't matter. It always will do with both without distinction. It will produce, in this case, 3 products, right? One product with this one, which is achiral, and then this one that is actually chiral. So you will get 2 products from this one, addition here, because this one is chiral, is prochiral, then it will give you two particular products, right? So which the other product will be with the dash. Okay, so you will get, in theory, you will get 3 products for this particular reaction. Is the same thing going to apply if I do HBr peroxide? Yes, exactly. You will get exactly the same products. Why? Because HBr peroxide is anti-Markovnikov. But in this particular compound, there is no anti-Markovnikov carbon. They're both Markovnikov, they're both anti-Markovnikov. Then HBr will add to both. Okay? So you will get exactly the same products with the HBr peroxide for this particular compound, because there is no Markovnikov center. There is no anti-Markovnikov center. Okay? So good. I just wanted to make that parenthesis so there is no confusion for if you guys see later on different reactions. Okay, so let's continue with this one is the mechanism. I mean, we already went over that. The alkene is electron rich. It will attack the hydrogen that has a delta plus. Bromine is delta minus. Then you have a carbocation. The carbocation can potentially give you a CCR, but in this case, you don't have CCR because a tertiary carbocation, the bromine attacks, and then you get one single product. In this case, because your carbon is not prochiral, but sometimes you might have a prochiral chiral center. Here's what it says. So if you guys have a carbocation that can be prochiral, definitely you will get 2 enantiomers. In this case, they are enantiomers because that is the only chiral center. But just to be safe, include the word stereoisomer. What's the reason? We already went over that, right? That the carbocation has a p orbital that has 2 lobes. So the nucleophile can attack each lobe, giving you each of the enantiomeric forms of the product. Okay, good. It also sensitive to rearrangement, CCR. That reaction, anytime that you guys do carbocations, you guys will have a CCR opportunity. Always watch out for that. The hydride shift is prioritized, right, over the methyl shift, ethyl shift. What if can I do ring expansion here? Yes, you can also do ring expansions as well in this particular compound. Remember, the rearrangement happens. If your carbocation has the opportunity to improve the stability of a cyclic compound that is under strain, for example, propane, butane, right? So those highly strained rings, definitely you will do it. The molecule will always find the opportunity, the right opportunity to gain stability. So if it forms a carbocation, definitely it will use the carbocation to gain stability in the case of cyclobutane or cyclopropane. Okay, great. Hydrohalogenation rearrangement, yeah, the rearranged product is always going to be your major product. Okay, so it is not specific, it is selective. It will always give you the rearrange. So you will get both products without rearrangement and with rearrangement, but the rearrangement will be your favorite products, right? Now, in your reactions, Professor, do I have to show all the possibilities? No, you always have to show only the major product. Don't really focus, I mean, in the other products, unless a question tells you, write all the possible products. In that case, you have to write them, but most likely I will only ask you for the major product, okay? Which in this case, you guys know that it is the rearranged product. Okay, acid catalyzed, next reaction, right? So now we are going down on the list. We have now the acid catalyzed. Now what we are doing is the hydration. This hydration, and then I'm gonna turn on my, it's one of the most important reactions, very useful reaction. Let me stop sharing. I don't know how to do something with this focus. Okay. Hydration reaction. The purpose of the hydration reaction is to add water to the alkene, right? To add water. H goes to one and OH goes to the other one. So the hydration reaction, the goal of the hydration reaction is to make alcohols. Okay. What is the goal of the hydrohalogenation? Is to make alkyl halides. In this case, I'm making an alkyl bromide, right? Alkyl bromide, alkyl bromide. In my previous examples, I was making an alkyl iodide. Here, I was making, what is my chlorine? Here, I made an alkyl chloride, right? So here, all the hydrohalogenation is to make alkyl chloride, bromide, and iodide. No fluoride. You can make any of those, okay? So it's very important you guys come up with your own list. It's like, what is the purpose of hydrohalogenation? Hydrohalogenation allows me to make alkyl halides. What about hydration? Hydration reaction allows you to make alcohols, okay? You will make alcohols out of the hydration reaction, okay? Now, hydration reaction can happen in three different ways. Three different reactions is the acid catalyzed. That's one of them. The other one is oxymercuration. And the last one is hydroboration. I know those names are weird, right? Okay, so what is the difference out of those two? Out of those three reactions? They're all hydration. They do the same thing, alcohol. The difference is the reaction conditions. Which one follows Markovnikov? Acid catalyzed follows Markovnikov? Yes, it follows Markovnikov. Oxymercuration follows Markovnikov? Yes, it follows Markovnikov. Hydroboration follows Markovnikov? No. This is actually anti-Markovnikov. That's the difference between hydroboration and these other reactions. Then what is the difference between catalyzed and acid catalyzed and oxymercuration? Is the fact that you guys can do rearrangement, rearranges. Okay? Or it can be potential CCR. Acid catalyzed, yes, you can do rearrangement. What about oxymercuration? No, it doesn't rearrange. It doesn't go through carbocations. Acid catalyzed uses carbocations as an intermediate. Oxymercuration does not use carbocation as intermediate. It does not rearrange. There is no carbocation here. Here there is carbocation. What about hydroboration? Also rearranges? No. Hydroboration also never rearranges. Okay, so that's another difference between hydroboration. That's basically a table that summarizes all the hydration reactions. Acid catalyzed is Markovnikov, but you have the risk of rearrangements. High oxymercuration is very stable. You do Markovnikov without arrangement. So whenever you see the alkene, it will do it right there. It won't move. If you do this, yes, it might move. This hydroboration, the only specific thing is that hydroboration is anti-Markovnikov, right? Okay, so based on that, let's do the hydration reaction. Now, since I have the camera right now here and it's focused already, so let's do the acid catalyzed hydration mechanism. Okay, acid catalyzed hydration. So let's say that I have this alkene, and then I do H3O plus in water. Now this H3O plus is a general acid. But what is the common acid that is used for that? You normally use sulfuric acid. Okay. What else is? I have seen also that people they use phosphoric acid. They are strong acids. Okay? Can I use HCl? It's an acid as well. No, don't use HCl. Why? Because if you use HCl, you are going to compete hydration with hydrohalogenation. Remember, HCl, we used it for hydrohalogenation. So don't use it for hydration. Okay? Can I use nitric acid? No, don't use nitric acid. Why? Because nitric acid is an oxidant. So you have to use an acid that only plays as an acid, not as an oxidant. Nitric acid is an oxidant. Hydrochloric acid, the chloride also reacts with the alkene, so I don't want to use it. Sulfuric acid is good, phosphoric acid is good, because these guys are not nucleophiles. Here, this one is nucleophile. This one is an oxidant, that's why it's not used. Okay, so for acid catalyzed reaction, only use sulfuric acid or phosphoric acid, not both, only one of them. By convention, I have seen mostly sulfuric acid, but it's catalytic amount. Remember, it's catalyzed. What does that mean, catalytic amount? That means that I use pure concentrated sulfuric acid? No, you only use drops of it. It's only catalytic amounts of what you put. Okay, so let's do this reaction, this mechanism. Let's say that they tell me H3O plus in water, write the mechanism for this particular conversion. Okay, so let's do it. So the reaction starts by the catalyst, HOH2 plus. What is this, Professor? This is H3O plus, just written in a better way for the mechanism. You can see OH3, right? H3O plus. Just written in different ways. The alkene attacks, is electron rich, attacks the hydrogen, and the oxygen leaves. Remember, it's always electron rich to electron poor. Here I have electron poor, delta plus, right? Then the oxygen has electron delta minus. So the alkene attacks. This reaction is Markovnikov. Therefore, the carbocation should go to the most stable carbon. My most stable carbon is this one. So the H will go there and the carbocation will be here. The H should be somewhere here. Right? Now, I have to ask if this carbocation will do CCR. As soon as you form the carbocation, you have to investigate CCR. Secondary carbocation, secondary carbon, primary carbon, no CCR. Then who has to attack? The nucleophile. Who is the nucleophile? Water. Water is the nucleophile. So water will attack the carbocation. It's prochiral, right? It has an ethyl and a methyl. It's prochiral. So that means that the water can attack in two lobes, but I don't need to show it in the mechanism. So I will have OH protonated. Why protonated? Because the water is added as a neutral compound, right? So once it adds, I get a water protonated, right? A water, sorry, with a positive charge. So I cannot leave it like this. Anytime that they give you a mechanism, you always have to get exactly the same molecule you are being asked for. Okay? So in this case, OH neutral. They didn't tell me OH2 plus. Okay? So I have to give it like that. Oh, Professor, what happened with the other product? Should I also draw the other product? Yes, you also obtain it. You also make it. But it's both of them, right? They're the same thing. So you don't have to show the mechanism for both of them. Just show for one of them. In this case, I'm using the wedge because here in the equation, they gave me the wedge. But if here they give me the dash, well, I will use this one. I'm going to use that. So how can I polish that? How can I clean this up, right? Basically clean it up. I can use water, more water. The water can take care anything that has electrons. In this case, water. The water has electrons. So water will take that hydrogen and the bond goes back to the oxygen. OH. Okay. What happened with this water? Okay, H3O plus. Good, because that's my catalyst. Remember from Gen Chem 2, catalyst participates in the reaction, but is supposed to be regenerated at the end. I use at the very first step H3O plus, and in my last step, I regenerated H3O plus. So the acid was used during the reaction, but then it was recovered at the end of the reaction. I didn't spend it. That's why I only need drops, because it's only to activate the study reaction. I don't need it for anything else. The acid is not lost. Okay, so you guys will have the acid, right, as a side product, but it is really not a side product. It is the catalyst. It was only that it was regenerated, and then you guys produce your alcohol. This is the conventional addition reaction, acid catalyzed hydration. Let's do one with one example, one mechanism with migration. Okay, so let's see. I have this alkene. Okay, let's do that one. And they give me you have diluted. Sometimes you will see that diluted sulfuric acid in water. Okay. And they say that you obtain this particular compound. Okay, great. Write the mechanism for this reaction. Okay, so I can see in this reaction that the OH, right? I would expect the OH to go here because that's my Markovnikov. Acid catalyzed hydration is Markovnikov, but I'm not seeing Markovnikov. The OH pushed, right? Was pushed to the left. So why is that? That means that it went through a CCR. Okay, so let's see what happened to the compound. Acid. You can write it like that. Can I do H3O plus? Yeah, you can do H3O plus. Remember that sulfuric acid in water or when it's diluted, it creates H3O plus. It doesn't matter. So here in my previous example, I show you the mechanism with H3O plus, but you could also use sulfuric acid like this. So alkene attacks, right? Attacks sulfuric acid. This is Markovnikov, meaning that the carbocation has to be formed on the most stable carbon. This is Markovnikov. What happens with bisulfite? Bisulfate is just hanging out there, nothing. But remember that you also have water in the system, right? According to the reaction. Okay, next is anytime that you guys produce a carbocation, you have to explore CCR. In this case, can I have CCR? Secondary carbocation, primary carbon, tertiary carbon. Yes, I do have CCR. So the CCR will lead from the tertiary to the secondary carbocation. Okay, so if I move that hydrogen, now I will have the carbocation on the tertiary carbon. Tertiary carbocation. Any other CCR? No, no. I don't see any tertiary. Any other tertiary with resonance or a better carbocation than this one. So then I go next with the nucleophilic attack. Nucleophilic attack, oxygen attacks the carbocation. Is this carbocation prochiral? No. This ring is the same as this ring, so it's not prochiral. So I get only one product. So the oxygen is positively charged, right? Because remember, I'm adding water. Okay. So I have to polish that one. What can I use to remove that hydrogen? Can I use bisulfate? Yes, you can use bisulfate. But is it better if you use water? It doesn't matter, to be honest. Any of the two can be used. You could say like, oh, I think it's better bisulfate. So if I use bisulfate, I could regenerate the catalyst, sulfuric acid, but it doesn't matter. Honestly, I prefer water. Why? Because water is more abundant. It's a solvent. So definitely the probability that water extracts that hydrogen is higher than this the bisulfate. Remember, you only added 1 or 2 drops of this. Here is milliliters. So definitely this one will be more likely to do it. But if you do it with bisulfate, don't worry. I mean, it counts also. It will be a right answer. Okay, so water takes off the hydrogen. This bond goes back to the oxygen as a lone pair of electrons. You guys the compound, right? Plus H3O plus, which is your catalyst, right? The catalyst is right here, is the acid, and you get this compound, which is exactly this compound. The compound is not chiral, so it doesn't matter where the OH is up or down, so it doesn't matter. Okay? So that's the mechanism with the acid catalyzed reaction. Okay, so let's go back to the PowerPoint. All right, so acid catalyzed hydration overview, it follows a Markovnikov. It's a radioselective Markovnikov. Is, as he says here, sulfuric acid is a commonly used, right? Sulfuric acid is a commonly used catalyst. Once again, normally I have also seen phosphoric acid, but sulfuric acid works as well. You use definitely water. That's the one, that's how you're gonna have the hydration. It's just the catalytic amounts, that means that it's only drops. That's the mechanism. It's very exactly the same as the mechanism I was showing you. The alkene attacks the hydrogen of the acid, forms the carbocation Markovnikov, and then that carbocation Markovnikov is attacked by the water by a nucleophilic attack. And then you guys have to deprotonate it, okay? So nucleophilic attack produces an oxonium ion. What is that oxonium ion? That OH2 plus, which is deprotonated. You have to deprotonate it. If not, the reaction is not done. You have to deprotonate it with water. Water functions as a base and deprotonates oxonium ion. Yeah, so you use the water because it's more abundant, as I was telling you, to afford the alcohol product. I need to have the alcohol as a neutral form. It's not as an oxonium ion form, right? So don't forget about that. This one is actually a very good slide because this one connects the chapter 7b and this particular reaction. Remember in chapter 7b, we were having an alcohol, and if you mix it or make it react with concentrated sulfuric acid, you create an alkene. This one goes through an E1 reaction. with sulfuric acid. Now, what we are doing is the opposite. What's the difference? Here I'm using sulfuric acid in both cases, yes. But here, in this way, to the alkene direction, is you are using concentrated sulfuric acid, high concentration of sulfuric acid to dehydrate. Here, you're using diluted sulfuric acid. So there is more water than acid to hydrate. So this way to hydrate and this way to dehydrate. Okay, so both ways you can do it with sulfuric acid. All what you have to do is only to change the concentration. Okay, so if we are synthesizing an alcohol, use excess water. Yeah, because you are hydrating. If you are synthesizing an alkene, you have to concentrate acid because you have to dehydrate. Okay? So it's both the opposite using the Le Chatelier principle as it says in this slide. So this hydration, it is carbocation. The carbocation can take you to a CCR, but also because it's a carbocation, you can get a potential racemic mixture, right? So a mixture of RNS or stereoisomers can be produced. That's what we are seeing here, that the OH is occupying here a wedge and here the OH is occupying a dash, right? Depending on what type of, right? If your carbocation is prochiral or not, or your product is chiral or not. Okay. Markovnikov hydration has limited application. Rearrangement often occur, right? As I show you in my mechanism, right? So there's nothing we can do to avoid the rearrangement. Carbocations are like that. That is a property of carbocations. They rearrange. That's their nature. They want to be more stable. That's why they always target or they are always pointing towards rearrangement. What to do if I don't want to do rearrangement? Then what you guys have to do is oxymercuration. Oxymercuration, the reaction is called oxymercuration, but it's really followed by a demercuration reaction. We're only going to see the mechanism, but just briefly, I'm not going to go over the oxymercuration. All I'm going to do is just explain you why oxymercuration does not give you rearrangement. Okay? This is the alternative, right? It's a good alternative for hydration as it catalyzed because it gives you no rearrangement. Okay, so let's see on the paper. I think you guys know that I work better with the paper. All right, so what to do if I have this particular, right, this particular alkene. I'm gonna focus it, just give me a second. Okay. If I want to do this. What if you tell me, oh, I want to produce this? Can I do acid catalyzed hydration? No, because if you use high acid catalyzed hydration, you are not going to obtain this alcohol. What you guys are going to obtain instead is this one. You're going to obtain this particular compound. Why? Because this one gives you CCR. You can do the mechanism for this, how you obtain this. You do a method shift here. Okay? So what to do if I don't want CCR? So what you guys are going to do is oxymercuration. In oxymercuration, there is no CCR. That's great. If there is no CCR, that means that there is no carbocation. How come? How come you have no carbocation? Because you use mercury as an intermediate, as a mediator. Mercury is the one that's going to get sacrificed. That's why the reaction is called oxymercuration, because you use mercury. You might wonder, oh, professor, but after so many years, how come, right? How come you guys still use mercury in organic chemistry? We know that mercury is so contaminating, is so toxic. Even from the organic chemistry labs, we eliminated mercury thermometers, right? If you guys go to any organic chemistry lab or any chemistry lab really, you are never going to see mercury thermometer. They were very famous, they were very popular. But how come they are gone? Because mercury is very polluting, it's very toxic. It can be easily absorbed by your skin. You don't really have to inhale, you don't have to digest it, you don't have to intake it through the mouth. Just by touching mercury. People playing with mercury, you can get contaminated. Why? Because mercury has a high affinity with organic molecules. So the size, the chemistry, the orbitals of the d orbitals of mercury, they make it have a high affinity with our skin. The oils, the lipids that are in our skin, the proteins, they have a high affinity with mercury. So mercury can actually be transported inside of my body through my skin. So it has a high affinity. That's why mercury is so toxic. It's one of the top heavy metals are mercury, lead, and chromium. Those are the, oh, arsenic. But arsenic is a more a metalloid, right? So mercury, lead, and chromium. Carcinogenic. Chromium is carcinogenic, 100%. Lead has some like neurological, right, effects in the body, also carcinogenic. And then mercury, highly carcinogenic, and also has a physiological effect in your body, and is immediate, the symptoms if you ingest mercury. So be very careful with mercury, please. Don't even try to open any battery. Battery are really like the Pandora boxes. They have a lot of heavy metals inside, right? All right, so let's go back to the oxymercuration. No CCR, no carbocation. So that means that there is no, it follows Markovnikov. So it adds here. I'll just explain you. I'm not going to do the full mechanism, but the reaction of oxymercuration includes mercury acetate. This OAC means acetate. Okay, so don't worry about the structure of acetate right now. It's just the anions, right? Imagine that there are like chlorines, chlorine, but they are just called acetate, OAC. Mercury has is a transition metal, so it has some electrons. So what is going to happen here is that the mercury, since it has a high affinity with organic compounds, will donate those electrons to the alkene, to one of them. So it will donate it to this carbon, and the alkene will form another bond here. Okay? So the lone pairs of the mercury form a bond here, and the alkene, the pi bond, forms another bond with the mercury. That creates this compound. Oh, one acetate leaves. Okay, you form this one, this particular species. This is called the mercurinium. I know it's a very ridiculous name, right? Mercurinium. Mercurinium ion. It looks like a cartoon name, right? Mercurinium ion. So you can see here, right? Is there any carbocation here? No. Where is the plus charge? The plus charge is in mercury. Mercury holds the plus charge. Can mercury plus do CCR? Never. You will never do CCR on a mercury. It is not eligible. It's the only ones that are allowed to do CCR, as the name says, carbocation rearrangement, carbo. So it's only carbon, the one that can do rearrangement. In this case, mercury sacrifices to be the plus charge. Previously, we were having a carbocation, right? If you do catalytic hydration, you guys will have a carbocation. This one can do CCR. In this case, you can do CCR. So what happens next? What happens next is water. Water attacks in the Markovnikov position. Okay, so basically what mercury is doing, mercury is holding the alkene. Is basically hugging the alkene, saying like the reaction has to occur here. So let's hold it here. It's like somebody doing the line for you when you guys are buying something, right? So the mercury is holding the line for the water. Why? Because if mercury doesn't hold the line, the carbocation can move anywhere. So here, that's the job of mercury, to trap the carbocation. Mercury will say like, no carbocation. Here's where the reaction has to occur. And then that's when water comes in and attacks on the Markovnikov side. Once it happens, the mercury withdraws, right? It leaves the mercury, but already the water is added to the Markovnikov without option of CCR. That's what happens in oxymercuration. We don't need to know the system. You guys don't even need to know this reaction, what happens. I just want to explain you why this reaction occurs without CCR. There is no CCR because the one that holds the positive charge is the mercury. The mercurinium ion is the one that holds the plus charge, breaking any opportunity for CCR. Since the mercury holds the plus charge, it makes space for the nucleophile, which is water, to attack in Markovnikov without rearrangement. Yep. So let's see on the slide. The slide is more graphic. Definitely they use more illustrations. Okay, so that is what happens with the mercury acetate. Here you have the mercuric cation. That mercuric cation, that's the acetate, by the way, OAC. It is this ion, is a carboxylate really. So So what happens here, you can see the reaction, right? So the alkene attacks the mercury, and this that bond, right, that lone pair of mercury closes the carbocation, forming a three-member ring. This one is the mercurinium ion, which is not rearranging. Okay? So now then the nucleophile, which in my case is water, because I'm doing a hydration, the water opens up in the Markovnikov position. Opens, the mercury is hanging there, but the water is already inside. It's in Markovnikov, so the reaction is done. So now how can I cleave? I don't need this mercury. So that's why you guys add sodium borohydride. You guys don't need to know that reaction. Okay, so just to summarize, the reaction, right? Because I didn't tell you what is the reaction conditions. And unfortunately, we have to know it, guys. I know it's a lot of reagents, but the reaction is mercury acetate with water, followed by sodium borohydride. That's the reaction conditions. So mercury acetate, HgOAC2 with water, that's your nucleophile, and you guys will get this compound. Remember that wavy line, right? The wiggly line means that you get both enantiomers, right? So R and S in this particular case with no rearrangement. What happened with the mercury? Is gone. I mean, is oxidized, right? I mean, it gets oxidized. This one, I mean, this one reduces. That means that this one gets reduced. I mean, I don't really know. I don't even know what is the fate of mercury after the reaction. It just goes away. It's soluble in water, so that's why it can be washed, right, with extraction, any of the purification techniques that we have learned in the lab. Okay, so these are the reaction conditions. Something that I want to tell you is that remember that here the hydration, right? This reaction with mercury uses water. So this one is your nucleophile. This one gets added here. What happens if I use something similar? Okay, so I use mercury acetate, water, sodium borohydride, right? That's the reaction. What if I use a different nucleophile? Can I do it? Yes, you can do it, but only I have seen it with alcohols. What about if I use methanol instead of water? Which is my nucleophile? My nucleophile will be methoxide. So what is the outcome? Now I will get OCH3. Interesting, right? I replace water with an alcohol, and then instead of getting OH, I get OCH3. I know how to make ethers. Now you guys know how to make ethers from alkenes. What if I use ethanol, right? Ethanol, you will get ethoxide here. What if I use terbutanol, terbutoxide here? What if I use here propanol, propan, right? Propoxide. Right? I like that name, propoxide. Okay. So you will make ethers. Here you will make alcohols if you use water, but if you use an alcohol, you will get ethers with oxymercuration. Can I do the same thing with the acid catalyzed hydration? No. The only one that gives you the opportunity is the oxymercuration. So oxymercuration can be used to make alcohols, which is really the real intention, right, for the reaction. But a small variant is to change the water by an alcohol, and you will make an ether out of it. Okay? So that's like an add-on to this reaction. Okay. So let's continue with the oxymercuration. We don't need to know the mechanism. Of course, we don't need to know the mechanism of the sodium borohydride. I mean, that's coming later. You actually will learn it in organic chemistry too. Okay, so in acid catalyzed, you guys will get two products, right? The non-rearranged and the rearranged. We know that this one is your major product. What about if you use to oxymercuration? That's actually the same example that I had for you guys. Oxymercuration, you guys will get this product without rearrangement. This is a chiral alcohol and both enantiomers are produced. Yeah, that's exactly what I was telling you, right? So both enantiomers are produced, a racemic mixture. So it should be like a wavy line here. Okay? You will get both enantiomers in this reaction. Okay, so we're done with the oxymercuration, the Markovnikov. Now we're going to do the hydroboration, which is the third third hydration reaction. The difference is that this reaction follows the anti-Markovnikov radioselectivity, meaning that it will be on the opposite side, right? So it's not going to be in the most attituted, it will be in the least attituted. If I have this alkene, of course, the anti-Markovnikov is this particular carbon. The reaction conditions are right here, BH3, THF. THF stands for tetrahydrofurane. Okay, the structure, I mean, you wonder how it looks like. That is tetrahydrofurane. It's a 5-member ring, and oxygen is part of the ring. It's a semi-polar. I mean, it's not too polar THF, but boron seems to be very soluble in this particular compound. I mean, that particular solvent. That's why it's used BH3, THF. That dot that you see in the middle, that means that BH3, because it's a gas, is dissolved in THF. Okay? So THF, which is a liquid. BH3 is a gas. It's like methane. Methane is a gas, right? It's a natural gas. BH3 is even more, is smaller than methane, so definitely it's a gas. So BH3 as a gas has to come up in a solvent. You cannot just use BH3. So as a gas, so it is dissolved in a solution of THF. And then in a second step, you guys use hydrogen peroxide, sodium hydroxide. Okay? The reaction is 90% percent yield, and you guys get the OH in the anti-Markovnikov site. Okay? Now, know that this is a 2-reaction sequence. What does that mean, 2-reaction sequence? Is that you have a step 1 and then a step 2. You are not putting all the reagents at once. That means that in my reaction container, I mean reaction vessel or beaker or flask, I'm not mixing all 4 reagents. No. First, you do the reaction with BH3 and THF, let it react, and then you add the hydrogen peroxide, sodium hydroxide. That is what that 1,2 means. Same thing here. Here you have mercury acetate in water. You let it react. Maybe we will do a reflux or something, right? A reaction. And then once the reaction is done, then you add the sodium borohydride in step number 2. Okay? So that's what it means, the 1 and 2. Now, the hydroboration is stereoselective, meaning that they will add in a same fashion. Okay? The anti-addition is not observed. What does that mean? Is a syn addition. Remember that what you are adding to the alkene is water, right? H and OH. Now there are 2 ways how you can do. Actually, I should. Right? That particular reaction is syn addition. Let's say I have an alkene, right here. So there are 2 ways how I can add the water. Right? Remember that hydrogen goes to 1 carbon, OH goes to the 1 carbon. I know that in this particular case, OH goes to the anti-Markovnikov because it's hydroboration. Hydroboration is one of the anti-Markovnikov reactions. But there are 2 ways how I can do this addition. I can do the addition syn, meaning that they both go from the same side, or I can do it trans, meaning 1 from the top, 1 from the bottom. In hydroboration, it's a syn addition, meaning that the H and the OH go on the same side of the alkene. Meaning that if you guys have a compound like this, right? So I do the hydroboration, BH3, THF, hydrogen peroxide, sodium hydroxide, right? 1 and 2. It will add, which one is my anti-Markovnikov carbon? This one is my anti-Markovnikov. Means that the OH will go there, okay? The OH will go, let's say, dash. That means that the hydrogen also goes dash. They have to be like that. What happened with this method? Well, the method has to be a wedge. You have to specify it. Do I have to be clear with this stereochemistry? For hydroboration, yes. For oxymercuration, no, because it is, you get an enantiomers, right? Sorry, the two products, wedge and dash. Here, no. Here it matters how they are being added. So in this case, OH and H, they have to be shown like this. Do I have a stereoisomer? Yes, you have a stereoisomer. The stereoisomer would be, actually, yes, you have a stereoisomer. You will have the OH wedge and the hydrogen also wedge, meaning that the methyl now is going to be a dash. You will get both products. Are these products enantiomers? Let me see. Yes, they're enantiomers. Yes, if you flip this, they will be the exactly the mirror image of this. Yes, they're enantiomers. So in this case, I would say like this plus the stereoisomer. In this case, they are enantiomers, but it's not always going to be the case. So the only time that you guys have to be careful about the two things that you are adding to the alkene is the hydroboration. The OH goes anti-Markovnikov. This one is the anti-Markovnikov. And the H goes Markovnikov, right? So, but they have to be cis. H and OH in as a dash or H and OH as a wedge. It's the only one that you guys have this in addition. Okay. Well, actually, you guys have the dihydroxylation cis as well. But that's coming later. But so far, that's what we have for hydroboration. Okay. Do we need to know the mechanism for this reaction? The mechanism is actually complex. You can see here, they even make it in very small fonts. But yeah, in general lines, just to tell you why is it anti-Markovnikov? Because the one that you are adding is the boron, right? The boron adds the hydrogen in a Markovnikov position. Because here you are adding a hydride. You are not adding an H plus. Normally you guys add an H plus. But here what you are adding is an H minus. An H minus is actually a nucleophile. So the nucleophile H minus, right? Here's the H minus, is being added to the Markovnikov. Right? If it's added Markovnikov, that means that the boron will occupy the anti-Markovnikov. And the OH will replace that boron. So really the OH, which is your real nucleophile, occupies the least substituted. Not because it goes against the rules. It's only because what you are adding is not H plus. What you are adding is H minus. Here you can see that is H minus. Let me erase it so you guys can see it. What am I adding? I cannot zoom in. Maybe can I zoom in? No, I cannot zoom in. What you're adding is the H minus. See, the H here with the bond goes here. So you're adding an H minus. So you're really adding a nucleophile first, and it goes Markovnikov. And the boron occupies the least stable. And then the boron, the BH2 is replaced by the OH. Right? So that really explains. Do I need to know this mechanism for the hydroboration? All these six or seven steps? No. It's just for your curiosity. I know you guys are very curious, so you don't need to know this, but it's only for your information. FYI for you guys, how it happens, right? What happens in the oxymercuration reaction. Okay, so predict the products of the following reaction. Okay, so I have my alkene. Let's do it here on this slide. Here in this one, I know the hydroboration is anti-Markovnikov. If it's anti-Markovnikov, here is where the OH will be, right? The OH will be there. I'll just make it really large. Nothing happens with the methyl, so the methyl will stay as a dash, so as a wedge. The OH will go cis, meaning that I will have here, and the H will be cis, and that methyl, right, will be a wedge. That's one addition. The other addition will be the methyl, nothing happens. Now the OH goes as a wedge, and the hydrogen also goes as a wedge, and the methyl now will go as a dash, right? So those will be my two products for this addition reaction. I don't really need to know. The good thing is that there is no CCR. Wherever you guys see the double bond, that's where the OH and the H will go. But remember that they have to go cis. They have to go cis. That's exactly what we had, right? Here they put it really weak, the H dash and the OH dash. H wedge, OH wedge, and H wedge. In this case, a mixture of diastereomers is obtained. Why are they diastereomers, not enantiomers? Because you have a second chiral center right here. That's why they don't call it enantiomers. Theoretically, they should be enantiomers, but because you have an additional chiral center, they are not enantiomers. They are diastereomers. Two chiral centers are formed. Why do we not obtain a mixture of enantiomers? Because you have an additional chiral center, and that chiral center does not invert. The OH and the methyl, these two are the only ones that invert. but this one never inverts. That's why you get a diastereomer, right? Remember, diastereomers are partial mirror images. Next, actually we're halfway. We covered already 1, 2, 3, 4, 5 reactions. This one is halfway, so if you want to take a break for the lecture, I mean, this one will be a good time to do it. Okay, okay, and then let's continue with the hydrogenation. You guys are gonna like this reaction. It's very simple, very straightforward. They use H2PT. So what we do is we erase, basically you erase the double bond. So you add hydrogens, you add hydrogen across the C double bond. It requires a metal catalyst. Normally it's just platinum, but you can also use palladium. I have seen nickel. Yeah, I think so. I mean, they use different alloys, nickel, rhenium, ruthenium sometimes, but the most common, don't complicate your lives. Use either platinum or palladium, PD. H2PD, normally it's very common to say like, what are you doing? Oh, I'm adding H2PD. H2PD means like hydrogen gas in supported on palladium or platinum, H2PT. Okay, so any of the two options works. An alkene is reduced to the alkane. You're producing alkanes from alkenes. That's the goal of catalytic hydrogenation. Okay, it's a cis addition. That's something that's very important. For example, you guys have it's a zinc addition. It's same as oxymercuration, but the difference is that there is no Markovnikov here. Why? Because you're adding HH. H to one carbon, H to the other carbon. So there is really no difference. You're adding two identical things. So there is no difference between who goes Markovnikov, which one goes anti-Markovnikov. But the only thing that we have to be aware of is the zinc addition, meaning that if you guys have an alkene like this, the one that you see here, the cyclohexane, if you use H2PT, the two hydrogens should go cis, meaning that the H dash and the H dash both. Right? You get these two. But this one is, this one will be enantiomers. Yeah, they are enantiomers. Yeah, they are enantiomers. You will get the two enantiomers for this particular case. These are enantiomers because they are like, if you flip this one, like if you turn this, you will get a mirror image of this other compound on the left. Okay, so remember that anytime that you guys add a hydrogenation, you guys are adding cis, those two hydrogens. Should I be careful if I do it in an open chain? Yeah, in an open chain is not, I mean, you don't really need to be that, I mean, that strict with the open chain. If I have an open chain, I'll show you an example. Okay. In an open chain, open chain. If I add here H2PD, right? All I just have to do is, that's it. Should I be worried about cis and trans? No. The only time that you guys have to be aware of or be careful with is in this case, in rings, because in rings, cis and trans are important. Okay, so you guys are going to be doing H2PT. Let's do here H2PT. Then in this case, yeah, you guys have to declare or to really state that they are added cis. Why? Because another option would be to add it, right? To have the one like that. But that doesn't occur. Only this one occurs. This one has an enantiomer? No, right? Because it's a meso compound. So it has no enantiomer. So that one would be the only product. Okay. Only take into consideration in a cyclic compound, this one, cis and trans. What about for the hydroboration? Yeah, for the hydroboration, the same thing. Only zinc addition is important, right? That restriction of the zinc addition is important only in cyclic compounds. In open chains, don't worry about cis and trans, right? So because I mean, remember all these bonds, they rotate. So if they are wedged, I mean, you just rotate it, they become dashed, right? So it doesn't really make any difference. But in a ring, it's important because you cannot rotate this bond. I cannot rotate this here, right? I cannot rotate it to make it a dash. No, because it's all part of a ring. So that's why in rings, it's important to be, right, to preserve the stereochemistry, right? Okay, so remember, any questions, please send me an email or ask me during office hours or I mean, anytime, even during the lab time. Feel free to come to me and then ask me about these reactions or these reactions. Okay, so the catalytic hydrogenation, well, what is the role of the metal? The metal, what it really does is reduces, right? Reduces the activation energy. You can see here how the high activation energy is, I mean, it's really, really high in value. But then once you guys use the catalyst, which is PD, PT, right? All those transition metals, that energy gets greatly reduced. Why? Because it changes the mechanism of the reaction. Here's really what happens. The metal surface, which is in this case platinum or palladium, right? The heavy metal, it binds, right? The hydrogen and the alkene. So it creates like a surface that is appropriate for the alkene and the hydrogen to interact. If you put hydrogen alone with alkene, the chances that they meet each other with the appropriate angle, the appropriate energy, the appropriate collision, the appropriate, right, like speed is going to be very difficult to achieve. If you add platinum, it gives a surface that makes the orientation of the two molecules appropriate for the reaction. The reaction is going to be successful. And here more or less shows you how this reaction is happening. Do I need to know this mechanism? No, you don't need to know this mechanism. Only know that the hydrogen gets adsorbed, right, on the surface of the platinum, the heavy metal, and then the alkene sits on it. And then by sitting on it, that's why you get a cis reaction, right? Because you guys have the hydrogen. Let me put it like this here. You got hydrogen, and the alkene is right here. So of course, the hydrogen will attach. That's why you get a same addition, because it's added to the same side. It's sitting on a surface. It's like when you put, let's say, like the staple, right? When you staple something, those two metal, right? The metal, when you put a staple. Right? When I put this staple, for example, right? They go cis. Right? These two, they go cis. So that's the way how it adds the hydrogen. The hydrogen, let's imagine that this one is my alkene, and the hydrogen adds cis, right? It's adding cis to the alkene. So that's the effect that I'm causing. Okay? So it's added that's how you form the bonds. Right? So that's really what happens. I mean, just to make an analogy, right, to the reaction of any cis reaction, really. Syn reaction. Next, hydrohalogenation. That one will be our reaction number 7. We're close. 4 more reactions. What are those 4 more reactions? Besides this one, we have halohydrin, the 2 hydroxylations, and then ozonolysis. Those are the 4 that are left. Halogenation. Halogenation is an addition of 2 halogen atoms across the CCC. That is a key word. Across. What does that mean, across? Across means that you guys will have it a trans addition. Trans. Across a double bond. It's not on the same side. Even though here it shows on the same side, but it's really not the same side. But you get this reaction in a high efficiency, 97% yield. This one is a key reaction, right, for the production of PVC. PVC is used normally for pipes, right, for pipes or the plumbing in your houses. All that plastic that is really hard that is used in the sinks, right, the drains. They're all PVC, polyvinyl chloride. Is done from the alkenes. Is normally used ethyl, which is called vinyl. This is called vinyl. And it has chlorine. It gets chlorinated. Then from here you can do a elimination. You get an alkene, and then you polymerize this. It's a polymerization here. We will see polymerization in radical reactions, so don't worry about polymers. You will see how plastics are made. We'll do that on chapter 10. Okay? So the reaction here. Halogenation is only practical with chlorine or bromine. Don't use I2, and of course, never do F2, right? So only chlorine and bromine. Halogenation with iodine is poor, and with F2 is too violent. Why? Because of the reactivity. It's too reactive, right? It's too reactive for the electron activity, the size, right? The electron density, too many things. I mean, many things going on with fluorine, as we know. The stereoselectivity is an anti-addition. Anti means that you get trans products. Okay, so you get the two in this case because these two molecules are they enantiomers? No. Let me see if I turn it. Yeah, they're enantiomers actually. Yeah, you get this one. I mean, you get the RS, right? You will determine. I mean, what is the relationship between these two molecules? If I flip it, or if I turn it, yeah, no, they're enantiomers. They're enantiomers. I'm just turning the molecule, and I think they're enantiomers. Okay, so you guys will get. I have to know the mechanism, guys. We have to know the mechanism for this reaction. So I'll definitely draw the mechanism for you for these molecules, but I just want you to know what are the details of this reaction. Okay? No carbocations, that's the good thing. No CCR, that's the advantage of this reaction. And yeah, let's go right through the mechanism, right? That's all what we want to see right now. So halogenation. As it says, halogenation is mostly applicable for chlorine, chlorination, and bromination. You get a dihalide. The purpose of this reaction is get a dihalide. Two halogens. This one is going to be crucial for alkyne preparation. That's what we're learning in this chapter 8, is because we will use it for chapter 9. Alkynes are made from dihalides, and then we learn how to do dihalides in on chapter 8. So we have an alkene. I use Cl2 or Br2, doesn't matter. And we get this compound. Trans. Okay, so what happens? Right? So the mechanism starts with the alkene. In the case of the bromine and the halogens in general, there is what we call an induced dipole or an instantaneous dipole, meaning that the bromine will get polarized, getting an instantaneous dipole moment. It's a very short time, right? But what happens is that the atoms, let's say like here I have a bromine, and here I have another bromine, right? So the nucleus are supposed to be in the center. But sometimes with bromine, since bromine actually bromine is a liquid, but it can be a liquid. I mean, if you heat it up, it will be the gas phase. It moves. So that means that maybe the nucleus of one bromine is shifted to the right side. What happens with the electrons? All the electrons will be here. So that causes that the electrons go on one side and the nucleus goes to the other side. That creates a delta minus delta plus in the molecule. So that's what is used in this reaction, is that the Br2 gets polarized Br plus and Br minus. I know that there is no difference in polarities or electron activities, but it is an instantaneous, temporary difference in electron activities, right? Or polarization. So what happens is that the alkene will attack the bromine. This one attacks the bromine. One of the lone pairs closes with the other alkene. That one creates that the other bromine leaves. Okay, so that's what happens. You create what we call a bromonium ion, very similar to what we saw before, Br plus. What happened with the Br minus? The Br minus is around. It's not far, it's right there. Okay, similar to what we saw, remember, for the mercury, the mercurium ion, right? The alkene attacks the delta, this one is delta plus, delta minus, right? The alkene recognizes that like temporary polarization of the bromine. The alkene attacks the Br that is delta plus, that ejects the bromide, and then to complete, right, the carbocation, that's when this lone pair of the bromine closes the 3-member ring. You still have those two intact lone pairs. You close it. What does that mean? That means now that your carbocation doesn't exist. What you guys have is brominium ion. No, they call it bromonium. Bromonium. The other one was mercurinium, right? Remember? Mercurinium. This one is bromonium ion. Brominium, no, no brominium, bromonium, bromonium ion. So that's why there is no CCR. Why? Because the bromine now is the one that holds the positive charge. Bromine does not rearrange, only carbon. So, but carbon now, that's why there is no CCR. Now, why is it? That explains why there is no CCR. Now, what explains that you have a trans, right, product or anti-addition? Because the bromide has to attack now, has to do the nucleophilic attack. But now what happened with this bromine? This bromine is covering one side of the alkene, right? The alkene used to be here. The alkene is right here. So the alkene used to be on this side. So what happened with the bromine, the bromonium? The bromonium covers one side of the alkene. That means that the bromide has to attack from the opposite side. Type of an SN2 reaction. Attacks the Markovnikov position, and then the other bromine withdraws, right? Leaves. That means that you guys will have this particular way of the attack. So the bromine goes at that bromine, the bromide attacks from the top, and the bromide goes to the bottom. That's why you guys have an anti-addition. The bromide was blocking this side, so the nucleophile has to attack from the opposite. So when it opens, they both end up having the opposite, right? The opposite directions. So that's why I put bromine wedge and the other bromine dash. That should be your product. Okay. It's important for us to know the mechanism. Yes, we have to know the mechanism of this reaction. I'll give you another one. There is no CCR. That's the good thing of this mechanism, is that there is no CCR. Here, I'll do it now with chlorine. Chlorine gets like a brief polarization, delta plus, delta minus. The alkene attacks the chlorine, delta plus. This one loses the chloride. And then one of the lone pairs closes the chloronium ion, right? There is a bridge, plus, and Cl minus, right? Just not to confuse, I'm gonna erase that plus. What I mean with the plus is and, right? And Cl minus. Okay, so that is my chloronium ion. It closed the bridge, right? The chloride is there. That prevents the carbocation arrangement because now the chlorine has plus. Now you say, like, oh, but how come chlorine holding a negative, positive charge? Chlorine hates to do that. Yes, it hates to do that. That's why this intermediate is very short-lived. So there is really not much, it's not too long. Okay, so which carbon should I attack here? Well, both carbons are both Markovnikov. There is no difference in substituent. They're both, right? They have both two branches, so it doesn't matter. So I will open this side. It has to be opposite. So you guys will have trans. If this one is a wedge, let's say this one is wedges, right? Are wedges. That means that the chloride has to attack from the dash side. That means that this chlorine will occupy the dash side, meaning that the other chlorine will be the wedge. And don't worry about the lone pairs of electrons. I'm just drawing the lone pairs of electrons just for clarity. But in your mechanisms, in the quiz or exams, you don't have to show the lone pairs. I mean, it would be ideal, but I mean, you don't have to. Okay, so here you show here if the chloronium ion is a wedge, right? The second chloride, right? The chloride has to attack from the dash position, and it opens up in the right. This chlorine plus now is neutral because he gained that this bond goes to the chlorine as a lone pair. So that lone pair, that bond now becomes this lone pair. Right? And the chloride comes with its 3 lone pairs, and you get that. Do I have to know that mechanism? Yes, we have to know this mechanism. Okay, that is the dihalogenation or dihalide. Is a dihalide formation. Now, since we are here, let's use this to also show you the halohydrin formation, which is our reaction number 9. 8, my bad. Yes, 8. Halohydrin formation. What happens in the halohydrin formation? It's very similar to this reaction. Okay, so what we have, guys, is that now we will have the alkene. We will have also the chlorine. but we will do it also in water. We will have water as well. Actually, it's not divided into steps. It's divided. It's only a thing is they are both combined. Let me double check. I don't want to give you a wrong information for the halide information. Yeah, it is both of them at the same time. Yeah, my bad. So it is chlorine in water. Okay. Okay, so what happens here? What you guys have here is chlorine and OH. This is what we call a halohydrin. In this case, would be a chlorohydrin. You get a chlorine or a halogen and an OH or an alcohol, right? It would be like a halo alcohol. Okay. Are they important? Yeah, they're very important in synthesis and also for us. Okay. I'll show you the mechanism, how it happens. Very similar to what we learned before with the with the dihalogenation. The first step is the alkene attacks, leaves, and closes the three-member ring. Okay, so the chlorine, right, is attacked by the alkene because this one is delta plus, delta minus. The alkene attacks that chlorine delta plus, loses the chloride, that's the chloride that is lost, and then one of the lone pairs of the chlorine closes the three-member ring. You guys hear the chloronium ion. Chloronium. Now, in our previous reaction, what we had is that the chloride opens, right? Attacks, that's a nucleophilic attack here. But in this case, we are not gonna do that. We're not gonna use the chloride. Why? Because we have another nucleophile that is abundant because it's a solvent, it's water. There will be a competition between chloride and water. Because water is the solvent, probabilistically speaking, water will be more abundant. Definitely the likeliness that it's gonna attack, it will be way higher than the chloride. So the water will attack and the chloride, the chloronium ion is, right, opens up. So what we will have now is that the chlorine, right, is a wedge. Now will be here as a wedge. And now here, the water attacks as a dash. The water wins over, right, beats the chloride. So, but I am stuck with this OH plus. I need to show it as neutral. So I have to polish it. Who can help me with that? Maybe chloride or another water. Doesn't matter which one. I will use water. You can see I prefer to do water. Water and then that one, right? It's a proton transfer. I get the product. That's what I wanted, right? So this product. This one is what we call a halide information. Here I'm doing with chlorine, but you can also do it with bromine, right? Bromine is also one of the eligible halogens, right, for the halide information. Okay, so let's go back to the slides. Br2 is non-polar, right? We know that, but is polarizable. Polarizable, right? So polarizable means that it can be dividing in delta plus and delta minus. Okay, so approach of a nucleophile will induce a dipole, right? So what's it cause? The nucleophile will be the alkene. The alkene causes that the bromine gets polarized. That's what it's telling us. Think of bromine as a bromine atom bonded to a good leaving group. Yes, that's exactly what it happens. You have here a Br plus bonded to a Br minus, and Br minus is a good leaving group. So it's actually going to leave eventually, right? So you get you put it that as a carbocation. I prefer not to think of it as a carbocation because if you put it as a carbocation, it will do CCR, right? This one definitely should do CCR because it's a carbocation. What really happens is this. So you guys have the alkene. The alkene will, right, the bromine, the alkene attacks, right, the bromide, the bromine plus, and the bromine, that will cause the bromide to leave. And then one of the lone pairs closes the three-member ring. Everything happens simultaneously, same way as I show you in my mechanism. You have the bromonium ion, the bromide has to attack, backside attack, basically. It's a backside attack, it's type of an SN2 reaction, opens up the bromonium ion, and then you get the two bromine strands, plus enantiomer, right? In this case, enantiomer. In the halohydride formation, it's exactly the same first steps, right? But now water is going to open up that bromonium ion. The water attacks, open it up, and then you guys have to take care of this, right? There are many more water molecules compared to bromonium. So attack the bromonium ion, water is more likely than bromide. Yeah, that's exactly what I was telling you, right? That water is the solvent. If it's a solvent, that means that the likeliness, right, that the nucleophilic attack to be done by the water is going to be higher than the nucleophilic by the bromide. So definitely attacking with water because in number is way higher. Okay, so that is a summary of the, well, not summary, the complete mechanism of the halohydride formation. You open up the bromonium ion with the water, you get the OH2 plus. That one has to be cleaned up, right? You have to deprotonate it. That one, in this case, they do it with water. Yeah, it's my preference as well. I will do with water. Can I use bromide? Yes, you can also use bromide. But I mean, you can see it's not preferred. Okay. So this one is a bromohydrin because you're doing bromine. And then in this case, it's chlorohydrin, right? Chlorohydrin is the one that we use. And it's combined without numbers. So it is basically chlorine in water. Here, we don't use step 1 and 2. No, it's chlorine in water. So both of them are added simultaneously to the reaction container. Okay, so it is Markovnikov. That is if it happens. Here in my example, I didn't have a Markovnikov, but the water is attacked to the most attituted carbon. So that means that the water will attack here to the Markovnikov position. So halohydride formation is a Markovnikov addition, meaning that the water attacks to the most attituted, right? The same way as a carbon. Even though it's not a carbocation, it will attack the most attituted carbon. Great. So now let's continue with the, now we have the dihydroxylation reactions, anti and syn dihydroxylation. We see an overview. So what we have in this reaction is we have an alkene, right? Sorry, have an alkene, and we will do a dihydroxylation, meaning that you guys will get a diol. That's the name for this. That's the name for this compound, diol. Okay? Diol means that two alcohols, right? So then they are vicinal or adjacent. Vicinal diols. That's what we are making in this particular reaction. Now, these vicinal diols can be done in two ways: anti or trans, and the syn, producing the cis product. Okay? So you guys have, we don't need to know the mechanism. We'll have formed an epoxide that's an intermediate for the anti-dihydroxylation, and for the syn dihydroxylation, we don't need to know the mechanism, but he goes over the mechanism. And for the other one is osmium tetroxide. It's expensive and toxic, right? But we use it for the cis dihydroxylation. In the lab, we also use permanganate, right? There's an experiment about TLC of isomers that it was done with permanganate, and you guys were getting the cis. In our lab, we also use oxone. Oxone works also with an epoxide. So this one, imagine this one is oxone, and he will give you a trans product. Okay. So these are the peroxy acid. The peroxy acid, one example is peroxyacetic acid, and another one is MCPBA, metachloropyrbenzoic acid. It's very common. This acid is a peroxybenzoic acid. It's a peroxy acid. I will summarize this. Here is the mechanism. We don't need to know the mechanism. You guys will do chemistry of epoxides in chemistry 240, the next class. So you don't need to know the mechanism. I'll just summarize. You can read about it. That will summarize these two reactions right now. Just give me a second. Okay. So here we will do the dihydroxylation. Dihydroxylation. We have two ways. The anti is with peroxides, NCPBA, peroxy acids. So let's say that I have this alkene, and I have a methyl, right there. And I use NCPBA followed by acid treatment. Okay, so you have to use it like that. NCPBA with acid treatment, otherwise it's not gonna cleave. That's how the mechanism works. I know it's kind of painful, but it is the technique is 1 and 2, not together. It has to be 1, 2. and you guys get this compound. You will get the OH and the OH trans. It has to be trans. It's an anti-addition with peroxy acids. Okay, so NCPVA can be replaced by the word peroxy acid, or you can also add RCO3H. Okay? Any of the three that you remember, NCPVA, peroxy acid, or RCO3H. They are both equivalent. That is the name in words. That is the abbreviation. And that's an example. That's an actual peroxy acid, NCPVA, metachloroperbenzoic acid, right? So that's the abbreviation. You get them trans, you get the both trans because in this case, you get the stereoisomer. But the important thing is that the OHs are trans. The OHs are trans. They have to be trans. That's what we get with this particular compound. No CCR, that's a good thing. No CCR, no rearrangement, right? But it's an anti-addition. Good. And the zinc addition is the other one. Zinc addition, we have two reactants for that. And so let's say that you guys have this, again, this cyclopentane, and I will do it with potassium permanganate, right, in basic condition. Has to be in acidic conditions. Right? So let me see, sodium hydroxide. Yeah, sodium hydroxide in basic conditions. That one will give you the OHs cis. Okay. That is one option. The other option is if you guys use osmium tetroxide followed by sulfide, right? So that is the reactant. Let me see. Let me double check with the osmium tetroxide. Oh no, you use a peroxide, an alkyl peroxide, ROOH. Yeah, that one. You use a NMO. I don't know what is NMO. I mean, I see the abbreviation right here in this slide, but I mean, it is an alkyl peroxide. Yes, here, alkyl peroxide. So osmium tetroxide, alkyl peroxide, and you guys get also the same products. Plus the stereoisomer. Okay, so this one is a reaction just to know. Potassium permanganate, osmium tetroxide, you get the cis, right? Cis diol, same result. Potassium permanganate in basic conditions, and this one is osmium tetroxide followed by alkyl peroxide. Here, if you want the trans diol, you have to use NCPVA, which can be also replaced by peroxy acid, the word peroxy acid, or the abbreviation RCO3H, followed by acid, and then you guys get the trans. Remember, you get both trans, right? The wedge dash and the dash wedge. Here, the same thing. In the cis, you get both dashes or both wedges, because they definitely will give you two, unless it is a meso compound, right? So it wouldn't be an enantiomer. So just be careful, I mean, without any stereochemistry, but this is a summary of what happens in dihydroxylation. Now, I will tell you, I'll just take the opportunity since I have the camera right now to do ozonolysis. I like to explain it better with words. I'm sorry, with my camera. In ozonolysis, as the name says, we are going to use ozone, O3. Okay, O3 is going to be used for this reaction, and glysis means cleavage. That's what we're going to do with the alkene. We're going to cleave it. Okay, so how is it going to happen? I mean, how is the cleavage going to occur? So let's say that you guys have this alkene. Okay? And you guys do ozonolysis. Step 1, O3. Step 2, DMS. Okay, it has to be DMS. What is DMS? DMS is dimethyl sulfite. That's an abbreviation. Another way how to write it is CH32S, dimethyl sulfide. Okay, so what happens here? The product for this particular reaction is this, 2 moles of this. Why? What happens? The easiest way for you guys to see it is that you guys take the double bond and then cleave it in the middle. Okay? If you cleave it in the middle, you will separate the 2 fragments, okay? The 2 sides, and then you are just gonna put oxygen there. That's it. That's all you guys do for ozonolysis. You guys can see that here I get an acetone, and here is also an acetone. That's it, what you guys have to do with ozonolysis. No mechanism. The good thing is that you guys don't have to learn the mechanism. This reaction has no CCR. And the best is that it has no stereochemistry. Okay? Why is it not stereochemistry? Because you do not generate chiral centers. They're all double bonded. Okay? That's one example. Another example, let me see if I find one. Yes. Okay. What happens to this compound if I do ozonolysis? Okay. If you do ozonolysis, cleave, right? Cleave the double bond. I'll make it longer. Okay. That's where the double bond used to be. And here I put an oxygen, and here I put another oxygen. Here is incomplete. What happened? Who is here? Here is a hydrogen. Okay, so if I want to translate that, it would be a better way to write it like this. Okay, so I will number it 1, 2, 3, 4, 5, 6, 7. 1, 2, 3, 4, 5, 6, 7. Okay, you cleave it. So you have a ring with a double bond. You open it up, open in an open chain, right? So sometimes you guys will get a ketone, sometimes you guys will get an aldehyde. For example, if it's a disubstituted, I mean, it's a highly substituted alkene, you will get a ketone. But if it only has one branch, you will get an aldehyde. Okay? There's a difference between the two. Let me give you another example. Okay, what happens here? If I do ozonolysis, cleave, you guys have 2 fragments. Okay? That's one, and the other one will be here. I have a carbon here. Don't forget that here is a carbon. So that carbon has H's. So here I will put a no, and here also put a no. What do I get? I get butanone, 2-butanone, and formaldehyde. Okay? I get 2 compounds here. Sometimes if it's an open chain, right? Open chain, you will get 2 products. If it's a cyclic compound, it's only 1 single product. Sometimes now you guys know how to make aldehydes and ketones. Okay? Remember, every reaction has a purpose. Ozonolysis, the job of ozonolysis is to produce aldehydes and or ketones. In the previous case, you guys were supposed to synthesize diols, right? Either transdiol or cis-diol. In halohydrin formation, you were supposed to synthesize an alcohol that is halogenated. In the dibromination, you're getting a dihalide, right? Every reaction will have a purpose. It's very important for us because then comes what we were waiting for. I know you guys were waiting for that question. We will start doing synthesis of organic compounds. Now I will show you how, I will give you an introduction of how this happens, right? Okay, so first let's go back to the slides. We're close to the end. I know this chapter is very long because it has a lot of reactions. Of course, 10 reactions is gonna take more than 2 hours, almost 3 hours, if not more. Okay, so this is the beginning, right, for auxiliary cleavage. Auxiliary cleavage is the ozonolysis. COO, CCC are also, CCC bonds are also reactive to auxiliary cleavage. That's why we use ozonolysis. Also is an oxidant. Ozonolysis is one of those processes. But since we are producing, one of the potential products is aldehydes. Aldehydes can easily get oxidized. That's why we protect the aldehydes by adding dimethyl sulfide, DMS. DMS protects them. An alternative, instead of DMS, if you don't want to use DMS, you can use zinc in water. That's another protective, right? A reducing agent that protects the aldehydes. Really The purpose of DMS is to prevent the oxidation of the aldehydes, because ozonolysis, ozone is so oxidative, right? It's such a good oxidant that it will also oxidize the aldehyde. But you don't want to oxidize the aldehyde. You want to protect the aldehyde. That's why you produce dimethyl sulfide and zinc in, or zinc in water. This one is an excellent way. So every time you go to the train, every time that you guys are about to go to bed, every time that you wake up in the morning, I know you guys have an outside life, right? Outside BMCC, outside your classes. But I would recommend you to get very familiar to this scheme. Can we use this scheme during the exam and quizzes? No, no, no. You cannot use those. Here we have a total of how many reactions? Here they have only 11. We should be, oh, here, because in reaction number 3, they have 2 reactions in one. Oh, here, the osmium tetroxide. Yeah, that's what I was looking for. Osmium tetroxide, remember that we were saying that we could use alkyl peroxide. You can also use sodium bisulfite. Bisulfite. That is NaHSO3 in water. You can replace that if you I mean, you remember that better than the alkyl peroxide, that would be good because it's inorganic. So you guys have to get familiar with this scheme. Take it, I mean, alkene with HX, give me an alkyl halide. Markovnikov, alkene with HBr peroxide, give me anti-Markovnikov. Hydration, right, with acid, with carbocations, right, Markovnikov. Oxymercuration, Markovnikov, no CCR. Hydroboration, anti-Markovnikov, no CCR. Zinc addition. Hydrogenation, H2PT, zinc addition, and then I create alkanes. Bromine is an anti-addition, no carbocation arrangement, no CCR, right? No CCR, and then I get an anti, right? The product is trans. Halohydrin formation, bromine in water. I get bromine trans to the OH, no CCR. Dihydroxylation with peroxy acid, trans, right? Anti-addition, trans product, the OHs are trans. Zinc addition of the dihydroxylation. Yes, you can do it with 2 ways. Potassium permanganate in sodium hydroxide in cold, or osmium tetroxide in bisulfite. Sodium bisulfite, you get zinc addition of the OHs. Next is ozone in DMS. You cleave the alkene and then you get aldehyde and or ketones. Okay, so that's an excellent summary of all the reactions. That's all I've been talking to you guys in the last 2-3 hours. Very useful information. So get familiar with this. I would say print this out, have it in the back of your notebooks, or take a picture, a screenshot. Always take a look at this reaction because this is an excellent, excellent summary. Okay, so that's for you guys for your own review. So if you're gonna practice to complete this chart, that would be good, so you know what reaction takes you to what. Okay, so that's actually for your practice. One extra synthesis, that's exactly what we were waiting for. So here, these particular slides, they will show the examples of how to approach synthesis problems. So we did a little bit of that on chapter 7b, how to synthesize, right, alkenes. But now, since we know more reactions from chapter 8, definitely 11 more chapters, 11 more reactions, we know more reactions, we can expand those syntheses, okay? So this is one step, addition reactions, right? A starting material is an alkene, and you add, right? You add another molecule. Substitution, you substitute X by Y, and then you have elimination reaction in which you just produce an alkene, right? So those 3 reactions, those 3 main brackets, right, of reaction will be used for your synthesis. For example, here, changing the position of a halogen. They give you this starting material and they want you to synthesize that. How do you have to think this? Okay, I see that my bromine in my last compound, right, my product, is internal, meaning that it's highly substituted, right? This bromine is in a highly substituted carbon. Here is in a less substituted carbon. What reaction allows me to put a bromine in a more substituted, meaning a Markovnikov, right? We know that more substituted is always a synonym of Markovnikov. What reaction allows me to do that? Okay, what allows me to do that is HBr. With peroxides or without peroxides? Without peroxides. With peroxides would be anti-Markovnikov. You wanted Markovnikov, meaning that is without peroxides. So I know that I have to do HBr alone. So I have to go back, right, to the analysis. Let's do it together then. I will copy the compound to show you how is the rationale. So how do we find out, right, what I have to do for each of these reactions? It's better if we do it together, right? All right, so what we have here, guys, is the reaction, right, that we were in question. So I know we started by saying that this one, right, my product is a bromine, that that has is a Markovnikov. Okay, so the starting material for a HBr, right, for a reaction with HBr is an alkene, right? I know that, right? So if I think that this one is going to be an HBr reaction, Markovnikov, I have to do that HBr on a particular alkene. So this alkene can be in different positions. It can be here, it can be here, or it can be here. Where is that alkene going to be there? Where is it going to be? Is it going to be here, here, here? The study material can give me a hint. Where is that hint? The material is telling me that the bromine was originally here. That means that most likely the alkene used to be here, right? Because this one is where it used to be, and this is where I want it to be. So I want I want those two positions connected. How can I connect them? By an alkene. So the alkene will be here. If I put the alkene here, then there is no way I can connect it to that bromine because it's too far. If I put it here, same thing. So I need the alkene to be close, right? To give me the opportunity to really work with the molecule. Okay, so that's what I'm gonna do. I'm going to put the alkene. I know that I have to do an HBr peroxides, sorry, an HBr without peroxides. And then I know that that alkene has to be there. Okay. If I do here HBr on this alkene, I get this product, 100%. Well, not 100%, but major product, right? Always work with major product. Now, is there any way I can go from this particular compound to this particular compound? Okay, yes. How do I make alkenes? I make alkenes with E2 reactions. Oh, also with E1, yes, but for synthetic applications, let's only do E2 reactions, okay? Unless there is a CCR, but normally you guys won't see CCR. So just forget about E1 for synthesis, only focus on E2. E2, I have two ways how to do E2 reaction, Zaitsev and Hoffman, right? Those are the two reactions. What is this one? Is this Zaitsev or this is Hoffman? Okay, so if I see the bromine, I can form two alkenes, 1 and 2. This one will give me a less saturated alkene than this one. That means that this one is going to be my Hoffman and this one is going to be my Zaitsev. That means that I need to do a Zaitsev elimination. So how can I do a Zaitsev elimination? By using ethoxide in ethanol. What if I need to do the Hoffman? Then don't use that. Use terburoxide, right? If we connect it with chapter 7b. If you want this side, it has to be terburoxide, but I want it here. So I can produce this alkene. That's why I have to use Zaitsev base, ethoxide. Can I use methoxide? Yes. Can I use hydroxide? Yes. Can I use propoxide? Yes. Anything, but not terburoxide or anything bigger than that, right? So it's always backwards, the analysis. Do you notice how I did this particular synthesis? I started backwards one step. How do I make this? Okay, good. This one. How do I make this? With this, right? Here, how do I make this particular compound? With HBr Markovnikov. Okay, good. Back. How do I make alkenes? E2, Zaitsev Hoffman. Back, okay? Always back, back. So here in this particular synthesis, you have 2 steps. Sometimes it will be 3, sometimes it will be 4. No, normally it will be 3 or 2 or 3 steps for now. Let's go step by step, okay? So let's do another reaction. Let me see, very similar to that approach. Now I want to do bromine like this. I want it to bromine here. Okay. The skeleton is intact, six-member ring, six-member ring. The only thing that changes, right, is the BR internal to a BR terminal. So let's go backwards. What reaction allows me to introduce a BR less substituted? Okay, so for that, you say, Professor, I have the HBr, I have the HBr peroxides. Some of you will say like, oh, Professor, what about the BR2? No, because the BR2 give me the dihalogenated. I get two bromines. I don't need two bromines. I need only one. The reaction that allows me to introduce only one bromine is HBr. If I use this, I will get two BRs. Or what about the halohydrin? Yeah, you could. The halohydrin actually only introduces one BR, but it also gives you an OH. I don't see OH here. I don't produce a halohydrin. I have to do only whatever I see in the molecule. The molecule, I will see a bromine. So one bromine will be either HBr or peroxide. In this case, I'm adding the bromine in the less substituted carbon. Here is more substituted, here is less substituted. So I have to use hydrogen in HBr in peroxides. So I know that here is HBr peroxides. What is the starting material for that? Well, if the bromine is here, that means that the alkene has no other choice. It had to be here. Good. That was my starting alkene. Now, is there any way how I can go from this compound to this compound? Let's see. What is this compound? This compound is an alkene. Alkenes are made by E2 reactions. E2 can be Zaitsev or Hoffman. Which one is this? Okay, I see my starting material, which is a halide, right? A halide is here, is a substrate for elimination. I can form an alkene here, here, or here. If I look at this particular alkene, I get a disubstituted alkene. If I do it here, sorry, trisubstituted alkene. Try, right? 1, 2, 3. If I do it here, 1, 2, 3, trisubstituted alkene. If I do it here, I get a disubstituted alkene. Therefore, these two are Zaitsev, and this is Hoffman. I need the Hoffman, right? Because that's the alkene that I need. Okay, let's do the Hoffman. What basis for Hoffman? Terburoxide, interbutanol. And I get this, right? So if I start with this compound, if I do terburoxide, I will get this alkene, and on this alkene, I do HBr peroxide, and I obtain this particular compound. Good. Okay. So there are more examples on the slides. I mean, I don't really want to make this this video so long because you guys are gonna hate me. And then we're only on chapter 8. But let me see another change, another reaction. I have this compound, and I need to produce this compound. Okay. How do I do this? Right? It's another conversion. That's actually kind of interesting. What reaction allows me, right? Always start from the product. What reaction allows me to get a cis-diol? Cis-diol. Okay, for cis-diol, Professor, we learned that we can do the dihydroxylation with either potassium permanganate in basic conditions or osmium tetroxide followed by sodium bisulfite. Any of the two works. The other dihydroxylation is with NCPBA in acid, but the difference is that this one gives you a trans diol. I don't need a trans diol, I need a cis diol. Okay, if you need a cis diol, then use potassium permanganate or osmium tetroxide. Okay, great. So if I need to do that, let's go backwards one step. So I know that this one needs osmium tetroxide followed by sodium bisulfite. Aqueous solution, right? The starting material for that has to be an alkene. The alkene is between the two, right? The two OHs. That means that the alkene should be this. Good. Makes sense, right? That part. Going back, osmotic tetroxide here. All right, so now, is there any way how I can go from this alcohol to this alkene? Yes, there is one direct way to go there, okay? So one way how to go from alcohol to alkenes, right? Remember, alkenes can be done by E2, by either Zaitsev or Hoffman. But there is one reaction that we learned in E1 reaction, in E1, that can directly convert OHs or alcohols into alkenes. I don't know if you guys recall, concentrated sulfuric acid. Okay, so if I use concentrated sulfuric acid, I can actually directly get that concentrated sulfuric acid. You guys get directly there. But what if I don't remember that? Well, if you don't remember that reaction, then you guys will have to do the other path through E2. So how do I obtain alkenes from substrate? Yeah, this one is my substrate. Here it will be a Zaitsev alkene, and here will be a Hoffman alkene, right? Which one do I need? I need here, Zaitsev. Okay. So if I do Zaitsev, that means that I'm using ethoxide, right, in ethanol. With what? With a compound that has a good leaving group. Why am I putting this? Because this guy is not a good leaving group, right? We know that OH is not a good leaving group. So I cannot just directly add ethoxide here because this is not a good leaving group. I need to do something to this to make it a good leaving group. What is that something? What reactions have we learned that we can do to alcohols to make them a good leaving group? Tosyl chloride in pyridine. That one converts alcohol into a good leaving groups, which are called tosylates. OTS. So you take this alcohol, well, here will be a wedge. You take this alcohol, tosyl chloride, you get tosylates. In tosylate, you do the elimination, you get the alkene, and on this alkene, you do the dihydroxylation, the zinc dihydroxylation, and you get this compound. Now you might say like, okay, professor, but this one will also give you the two OHs in a dash. This reaction doesn't tell me that. That's okay. That's okay. As long as your synthesis produces it, even if it's in the presence of another enantiomer or another stereoisomer, that doesn't matter. Okay, so I want to see this one, yes. But you say, oh, but it produces two, not one. Yes, that's okay. As long as it produces it, that's a valid route. Now, also, you might say like, professor, this path has 2 steps. This path has 3 steps. Is there any difference in efficiency? Technically, yes. So this route is more efficient than this route. So students, I mean, you guys, if you do the long route, you won't be penalized. But if you guys do the shortest route, right, the path, you guys actually will get extra points, okay? So that's just for, I mean, that's an agreement that we have between us, right? So you guys, you won't get penalized if you give me a synthesis that has 5 steps. And then another student does it in 3 steps. Of course, this one is more efficient than 5 steps, but the 5 steps won't get penalized. The one that the students that do 3 steps, they actually will get extra points if you guys do the synthesis correctly. Okay, so this is the approach. Always back. And there's always more than one way how to do a synthesis. This is a clear example that you could do this path or you can do this path. They are not wrong. So that's why in my quizzes or my exams, if you guys see my answer key and you see a particular synthesis method that doesn't match yours, that doesn't necessarily mean that you are wrong. Maybe your synthesis is correct. I'm just telling you that synthesis can have more than one way to be done. Okay, I'm not going to show all the 10 methods for synthesis in an answer key. I will just use the shortest. I will show the shortest way how to do the synthesis. But that doesn't mean that your route is right. Your method is wrong. I will look at it and I will see how you do, and then you guys will get the grade based on that. Okay, so here there are more examples for synthesis. This one is the Zaitsev, basically the same analysis I was doing, Zaitsev and the Hoffman elimination. Here in this case, they needed a Zaitsev. Right? Basically the same method I was doing. Another one, consider the following transformation. Okay, so here, let's do the analysis. So my product is an OH, right? It's a hydration reaction. I can see this. It's a hydration. Why? Because I'm creating an alcohol. That's why I was telling you at the beginning. So whenever you guys learn a reaction, know what it is used for. So this, for example, hydration is used for alcohol synthesis. This is an alcohol. Okay? Alcohol are synthesized, but this one, I have an alcohol in a less substituted carbon. What reaction allows me to put OH in a less substituted carbon, or meaning OH in anti-Markovnikov? I have to do hydroboration. Hydroboration starts from an alkene. That means that my alkene used to be here. How can I make this alkene there from here? I have to do a Hofmann elimination. Why? Because this one is a less substituted alkene. Here will be my size F. I don't want the size F. I want the Hofmann. Let's see what they do. Okay, so they convert the alcohol, the starting material, with TS chloride pyridine. Yes, they make it a good leaving group, and they do a Hofmann elimination. Look right here, elimination Hofmann with terbutaoxide. That gives you an alkene less substituted. Then once you guys have the less substituted alkene, you complete it with an addition with a hydroboration reaction. Okay, so that is strategy. Always think backwards. And once you have that step backwards, you have 90% of the problem done. Okay, why? Because the rest of the job is just to synthesize that alkene. And that alkene can be done either by Hofmann or Sice-F. That's it. That's all you guys have to do. Okay. Another one, changing the position of a pi bond. They want me to change that. Okay, so what is this? This one is an alkene in a less substituted, right? Less substituted alkene. That means that I have to do a Hofmann elimination, right? It is a Hofmann elimination. How do I do a Hofmann elimination? With terbutaoxide, right? I have this particular alkyl halide, and I do elimination Hofmann right here. But now, how do I synthesize this from this? Okay, this one is a bromination, right? Or a hydrohalogenation. But this hydrohalogenation is anti-Markovnikov. Why? Because the bromine is being added to the least substituted carbon of the alkene. That is an anti-Markovnikov. Okay, so that's what they have to do. They do, what is the answer now? They don't have all these steps. Here they do addition, HBr. Let me write. Sorry for the delay. Okay, I have to do here HBr peroxides, anti-Markovnikov. I get this product, and once I have this product, I will use terbutaoxide to do the Hofmann elimination. Interbutanol, right? Bulky base. Okay, so those are examples. I mean, I already gave you 2 examples, so I mean that's enough material. Definitely, I will do more synthesis problems in the solve problem video. So please be in the lookout, right, for those problems. But the main message for this last 10 slide is really synthesis. I'm gonna be asking definitely synthesis in this exam number 3 that is coming for this chapter. Remember, exam 3 is chapter 7B, 8, and 9, right? So heavy, very heavy in synthesis. I want you, because this synthesis really needs you guys to be aware of all the reactions. It's 11 reactions. 11 reactions plus E2 plus SN1 plus SN2, right? So all those reactions I'm getting in this bucket, and then we are using all the elements of that bucket to do the synthesis. That synthesis problem still really tells me everything that you are learning about these chapters, because it gives you a strategy. It's really like a game, right? It's a game, it's a strategy. You need to know the mechanisms, you need to know the reaction, you need to remember the main purpose of the goals of each reactions, and then that really challenges you for this particular task. Okay, so definitely all my good vibes to you guys. I know it's difficult. I went through this. We all in science, pre-meds, I mean, all the ones that are in STEM, we went through this. I know it's not easy, but definitely, I mean, we will survive, as we always say. I know it's very easy to say from my side, but we finish all these reactions. It's not easy, I know, but I mean, definitely we will make it through, right? So please let me know you guys have questions. I'll be posting. I mean, I will have posted also the solve problem videos Let me know if there is anything else I could help you with regarding this particular chapter. Okay? So see you guys for chapter 9.